Hello? Not getting any microphone here. What's going on? Testing. Testing. I think it's using the wrong microphone. 1 second. Microphone. Default. Testing. Testing. Wait up. Testing, testing. Testing, 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 testing. Testing now. All right. No problem, Alec. Thanks for dropping by. All right, I think we're gonna get started. I'm not entirely sure this is the right microphone. Kind of sounds like it, but we'll leave it at that. All right, so welcome to another HooPost stream. Today we're going to be looking at a paper called How to Scale Your EMA. This is a paper 27th July 2023, so just came out relatively recent ago. This is a paper out of Apple. So Apple's not really known for machine learning papers, but we did read one of their papers last week that was about basically kind of a weird nerf diffusion model kind of variant. So they do have researchers there. In fact, they may even start hiring more people now that it's kind of a requirement for big tech companies to have an AI strategy. So interesting to see a paper coming out of Apple that is extremely mathy, and this is kind of fundamental research in machine learning and AI. So kind of a weird combination of company and topic. So EMA is exponential moving average, which we're going to get into, but it's basically an average. So that's this word. An average of what? An average of weights. So if you have a neural network fully connected, right? That neural network is composed of a bunch of little neurons, and for every single one of those little neurons, you have basically weights, which are these numbers. So you could think of any neural network, and here I'm just showing you a fully connected neural network as an example, but this applies to convnets and transformers and any other architecture you can think of. Basically, there's these little parameters which are called weights. There's other parameters such as biases. There's even more different types of parameters, but you have a bunch of these parameters. And that is what the average is over. The average is the average of a bunch of parameters of a bunch of neural nets that are all kind of similar. So let's say you had 10 different versions of this neural net, each with slightly different weights, and then you took the average value for all of those different weights, divided it by the number of neural nets, and you'd get basically an average of what the weight is for this little neuron within this neural net. So it's an average over a bunch of different neural nets that are all the same architecture of neural net. Okay, what is the M? The M means moving, so exponential moving average. So the average is moving over time. And it's moving over time because each of the different neural nets, of which you can think of it like multiple copies of this neural net. There's many of them, maybe across multiple GPUs. Maybe they're being fed different data. You could think of it that way. Each of them is changing slightly differently. So each neural net in this ensemble of neural nets, even though that's not the right terminology, but in this little group of cohort of neural nets, is receiving a slightly different batch of data and changing its values or its weights a little bit, and then you can take the average of all those weights. All right, and then finally, exponential. And the exponential here stands for the fact that only the most recent steps are going to have a big weight. So in exponential moving average, the more recent values are more important than the previous values. So if you had 10 copies of this neural net, they're all slightly different. The version of the copies of the neural net that are closer to you in time are going to have an exponentially more important for the average than the ones further back in time. Okay, so that's exponential moving average explained. And that might not make a ton of sense just right now, but this entire paper is about exponential moving averages and kind of how those come from maybe perhaps more simpler mathematical ideas and concepts, and maybe how we can use some of those older mathematical ideas and concepts to learn a little bit about EMA. So I think by the time you're done with this video, you should have a much better idea about what exponential moving average is. All right, so let's get into this abstract. Preserving training dynamics. So training dynamics just basically means the motion of things, and training dynamics is how things change while you're training a neural net. So this isn't specifying a very specific thing. It's more just kind of a high-level term saying things are changing during training, and those things are following some kind of behavior, and we'd love to know more about that behavior. Across batch sizes, they're trying different batch sizes. So you can have a batch size of 2, you can have a batch size of 32, you can have a batch size of 1,000. Is an important tool for practical machine learning as it enables the trade-off between batch size and wall clock time. So what do they mean here? So when you're training a neural net and you have a data set of 1,000 images, you can break up that data set of 1,000 images into batches of 100 and then feed it basically 10 batches of 100. And that'll take some amount of time. If you instead had a batch size of 50, then it would take 20 steps in order to feed that entire data set into the training process, which is one epoch. So there's a little bit of a trade-off between batch size and wall clock time. Generally, this is a bit misleading because I think the batch size is more a factor of what hardware you have it on. So the batch size comes down more so to what GPUs are you working with and how parallel is your setup, as opposed to how much wall clock time you have, right? Because at the end of the day, everyone's going to take all the hardware that they have available and then maximize it. So the wall clock time is more a result of the batch size you're using, which is more a result of your hardware. So hardware is kind of the top level design requirement, and that determines batch size, and then that determines wall clock time. So it's not like you're generally making a trade-off between those. How's it going, Azur Waderv? I don't know if that's actually how you say your name, but okay. This trade-off is typically enabled by the scaling rule. For example, in stochastic gradient descent, this is normally referred to as SGD. So if you ever see SGD, this is what they're talking about. One should scale the learning rate linearly with the batch size. So this is kind of true, but also not necessarily true. It's a should here, kind of denotes a best practice, but there's not necessarily some theoretical guarantee around that, right? If you're taking a big batch, you should maybe use a slightly smaller learning rate, is something we see, right? Where there was a paper called Don't Increase the Learning Rate, Increase the Batch Size. And basically what that's referring to is that if you have very small batch sizes, you're only looking at a very small sample of the data set. Therefore, any gradient descent that you're doing with regards to the signal in that small sample from the original data set is going to be more noisy. So the bigger the data set, or not the bigger the data set, the bigger the batch, the more representative that sample is of the entire data set distribution, which means that you can probably have a little bit higher learning rate and in that way end up at the right answer better. And kind of when I would say end up at the right answer, learning rate optimization, neural nets landscape. Let me see if I can get the GIF. I've shown this GIF before, but this one, I think this is the GIF. I love this. Open link in new tab. Ooh, I need the GIF version of this. Actually, this is a good thing, but you could think of any optimization process, right? These are just weights. So the same way that here we have, I don't know what this is, like 20 little neurons represent this neural network, and this neural network is really a set of 20 values, each of which represents the weight at one of these neurons. Here we have a one-dimensional neural net. So imagine if your neural net was just a single neuron that had a single value. Maybe if the value was this, you would have a certain score on your, so the x-axis here is kind of the value of the weight, and the y-axis here is your loss function or your score or something like that, right? So one value maybe results in a slightly higher score than a different value for your weight. So the whole process of gradient optimization is finding the value of the weight that minimizes some loss function, right? So you really want to find W12. You want to end up with a neural net where the weight is W12. And this is a one-dimensional example, so project that, realize that basically here's a two-dimensional example, so this may be a two-dimensional little neural net here, where the y-axis here, or the z-axis here would be the value of the loss function, so a lower point is better, and then the x and y here are the values of some weights inside a two-dimensional neural net that only has two values. And that's about as far as your brain can think. Like you can envision this because this is a three-dimensional plot, but realize that we're talking about, imagine if instead of x and y 2 dimensions, we had however many this is, 20 dimensions, right? And then now realize that this is an even simpler version of something like a ChatGPT, right? Which has billions of parameters, billions of little values, billions of weights, right? So for every single possible value of each of those weights, we're sitting at some point in this, what is sometimes called like a loss landscape. And what you're doing when you're doing gradient descent is you're moving around in this loss landscape. You're trying to find the lowest point that you can. But it's very difficult to do that because you're just taking these little steps, right? You're taking these little steps and you're changing the values of the weights. So you're just taking a little step over here, and then maybe you take a little step over here. And then slowly over time, you might find your way into this little minimum here. But you can also pretty much guarantee you're going to end up in local minima, right? I don't think they have an example of that anywhere here. But yeah, here. No, that's not the one that I want. Is this the GIF? Yeah, this is a GIF. So this is the GIF that I was looking for, right? So this is different optimizers, which are basically different ways of taking the gradient step. And you can see how some of them are a little bit faster at moving towards the lowest points on this loss landscape versus other ones take a little bit longer. But you can see how some of them overshoot. Some of them, see how this black one here, RMS prop, it kind of figures out that this is the way to roll down the hill. But this Nesterov accelerated gradients, I think that's what NAD is, or NAG is, and then the green one, which is momentum based, you can see how they overshoot a little bit. So gradient descent isn't taking you in the fastest possible way to the best possible solution. It's kind of wandering around a little bit. You know, you're kind of taking a lot of steps that maybe don't lead you in the right direction. Maybe they do lead you in the right direction. It's not entirely sure, and that's why neural networks are a bit of a black box. So in this paper, when we're talking about exponential moving averages and gradient descent, I think it's always useful for me to envision this. This is always kind of the image I have in my head of kind of moving this marble in this hill that represents the loss surface of a neural network. Okay. Just some random characters. Okay. All right, so let's keep going. Another important tool for practical machine learning, and the practical here just basically means machine learning that is applied in practice, so it just means machine learning where you're actually maybe trying to do something, which is kind of weird to kind of talk about because this is a very theoretical paper. It's like kind of like a basic fundamental research kind of paper, and they're talking about practical machine learning, so it's kind of weird. Is the model exponential moving average? Okay, which is a model copy that does not receive a gradient but instead follows its target model with some momentum. Okay, so what is the target model here, and what does it mean by model copy? So let's see if we can actually find a good picture for this. EMA model copy. Some of these, no, none of these are good. Okay, I'll just explain it. So, like I said, sometimes you have multiple copies of a model, right? So you might have your little neural net and you might have multiple copies of these. Maybe they're on different GPUs and they've received slightly different training data, which means that they're slightly different points along this in this plot, right? So maybe one copy is here at W5, another copy is here at W6, and then you have another copy here at W4. So what you're going to do is a lot of times people will create this EMA weight, right? So you can think of it, we're creating a new point here that's going to be the exponential moving average of these 3 points as they change over time during the training process. So maybe W4 slightly goes down, W5 ends up over here, and then maybe goes down, and we're going to have a point which we're going to call the target network, and that network is basically going to be the exponential average of the 3 copies that we have currently training. So that's called the target model, right? And follows its target model with some momentum. I guess that maybe in this sentence, the target model is the actual individual ones that are actually taking in gradients and moving around, and then the exponential moving average is going to be the average of those. This model, EMA, can improve the robustness and generalization properties of the supervised learning, stabilize pseudo-labeling, and provide learning signal for self-supervised labeling. Okay, so I think they maybe introduced a little bit too many concepts there, but let's go back to our ball on the hill. Yeah. So imagine if rather than one neural network with one set of weights, you had a bunch of neural network copies with slightly different set of weights. And imagine each of those as one of these balls on this loss landscape. So if you think of that, it should be kind of clear to you how an average of every single one of those balls would probably be better than any one of these balls individually, right? It would probably be a little bit more stable, right? If you took the average of these 6 balls here, or 6 little marbles that were moving down, the average is actually quite good. You know, it kind of like moves right in the right direction and kind of moves slightly towards the right thing. So that's kind of why this EMA can stabilize, right? So the key word there is stabilization, robustness. It just makes it easier. It makes this whole optimization process easier and more robust and more stable. And then self-supervised learning, pseudo-labeling, supervised learning. Those are supervised learning, for example, versus self-supervised learning. Supervised learning is when you have a specific target. So whenever your data set, for every input, there's an output. Self-supervised learning means you're either creating the output for every input, so some form of pseudo-labeling where you don't actually know whether this is a picture of a cat or a dog, but the network itself labels it as a cat or a dog, or self-supervised learning, which is the more kind of larger umbrella term, which involves any supervised learning technique where that label is coming by the model itself. So the problem is structured in a way that it creates the labels for itself. Okay, but the key word there is that exponential moving average leads to stability and robustness. Okay, prior works have treated the model EMA separately from optimization, leading to different training dynamics across batch sizes and lower model performance. Okay, so EMA being treated slightly different than optimization. What do they mean by optimization? Optimization generally refers to, for example, these are called the optimizers, right? And all of these optimizers here, usually they're not just a single algorithm. Usually these have little hyperparameters within them, right? So for example, the Atom optimizer PyTorch. When you use the Atom optimizer in PyTorch, you actually have to decide not just the learning rate, but you also have to decide other parameters such as these betas, this epsilon, right? There's all these little extra parameters that you have to pick when you're doing optimization. And some of these other optimizers here have different parameters and different values for those and different best practices. So here they're kind of setting up the idea that maybe EMA has some relationship to those optimizers. Maybe we should try to pick the value of those optimizer hyperparameters based on what we know from EMA. Okay. In this work, we provide a scaling rule. So this is going to be the kind of big part of this paper, for optimization in the presence of model EMAs and demonstrate its validity across a range of architectures, optimizers, and data modalities. Okay, so this is a kind of a fundamental research paper, right, where they're trying to show some fundamental property of machine learning and kind of neural networks themselves. So they want to basically demonstrate that whatever theoretical insight they're going to draw, it has experimental validity, right? So first of all, they want to say, okay, we're going to come up with this theory. Well, we want to show that it's true in practice. But because what they're trying to show is kind of a general concept, they want to show that it works for a bunch of different things, right? If they just only showed this for a fully connected neural net, it wouldn't have the same impact. It wouldn't hit as hard, right? So they want to show that it's going to work for a neural net. They want to show that it's going to work for a convnet. They want to show that it's going to work for a transformer, for natural language, for images. They want to show that it works across all the different data modalities: image, text, graphs, IMU, sensor data, whatever you want. All the different optimizers, so all these different optimizers here. They also want to show that it works for a bunch of different architectures like transformers, convnets, and so on. We also show that the rules validity where the model EMA contributes to the optimization of the target model, enabling us to train EMA-based pseudo-labeling and SSL methods at a small and large batch sizes. So SSL is just self-supervised learning, which they defined up here. Pseudo-labeling, a kind of self-supervised labeling or self-supervised learning. And at a small and large batch sizes, so they're going to be kind of ablating different batch sizes, see if you end up with the same behavior. For SSL, we enable training of BYOL up to batch size 24,576, 24576. That's kind of a weird choice of a number there, without sacrificing performance, optimally a 6-time wall clock reduction. Pretty important, right? And I think that this is one of the areas where fundamental research in machine learning can actually drastically improve all machine learning, right? So if we can find out something fundamental that applies to just the process of machine learning in general, maybe we can improve all types of machine learning and not just some one narrow specific niche like vision or text or natural language or anything like that, right? So that's the advantage of trying to figure out fundamental science versus narrow specific applied science, which I would say is a lot of the papers that we read are little tricks that really only apply to some specific type of diffusion model, right? And it's great, but it's only going to work for that specific type of diffusion model versus this type of paper. Hopefully this theory and this rule that they're going to propose here applies to all models, and maybe we can get a 6-time wall clock time reduction for all models and all data modalities. So BYOL, I think this is like a paper, build your own latent, bootstrap your own latent. So bootstrap your own latent is kind of like an older technique at this point, but the idea is that you would basically use kind of like an EMA, right, where you basically have a target network and then an online network. Here you go. Is this an easier way to do it? But you have multiple networks, and then you're basically trying to get all of the networks to produce the same latent. And in that way, you build this latent space that kind of has a little bit of agreement. So maybe this is an example. I guess this is the original build your own latent paper figure. So you have some image, you see some augmentations being applied to the image. Here you have a crop augmentation, and a left-right flip. Let's open this image in a new tab so we can zoom in a little bit better. So here you have a crop and a left-right flip. Here you have a more aggressive crop, and then you have some kind of grayscale or opacity change as well. And you see how they're both getting fed into a ResNet, which is kind of an older computer vision model at this point. Nowadays, we would use something like a vision transformer, but that's getting fed into a ResNet, which then here it becomes image embedding. And this is kind of a more classic way of doing computer vision, where you would have kind of what they would call an image encoder, and then you would have a model head here, which would MLP just stands for like a little neural net, fully connected neural net. Nowadays, we just kind of compress all of these 6 little rectangles here. We would just have one rectangle that says VIT, and then we would just have one thing that comes out of it. But back in the day, they kind of made this separation more explicit. And what I mean by that is that, for example, in a transformer here, maybe this one is the one I want. Open image in new tab. So you see, you kind of have similar kind of idea here. They're separating out this feed forward from the multi-head attention, and here in this paper, or in this figure, they're kind of doing the same thing. They're separating the ResNet from the MLP. But kind of getting distracted, really what BYOL is all about is that this cropped augmented picture of the dog has the same semantic concept as this cropped picture of the dog. So you would expect that in a very well-shaped latent space, right, that the latents corresponding to this should be not identical, but they should be very similar to the latents of this, right? Because these two are representing the same underlying semantic concept, which is this kind of like golden retriever looking like dog, right? So basically you're going to feed both of those through these ResNets, and you want the latents that come out of that, the representations that come out of that, to basically be similar. And there's an additional layer of complexity where you have basically a target network and an online network, where the online networks are the ones that are receiving gradients, and then your target networks are the exponential moving average of your online networks. And that's where the EMA comes into play here for the build your own latent. But I think that that's probably not, that probably goes beyond what we're going to explore in this paper. I think they were just kind of bringing that up as an example of something they could do, but to me, the more interesting thing is how this EMA interacts with different optimizers and kind of the theoretical guarantees that they're going to bring for that. So this paper is like super dense, and I'm kind of playing in my head about how I want to do this. I think if I read this at the level of granularity that I just read this abstract, we're going to be here tomorrow. So if you guys have any questions, let me know. I might try to like kind of skip through some parts faster. I might try to slow down and talk about things, but let me know what you guys want me to talk about. All right, so here with the introduction. With data and models becoming progressively larger, right? So not only are the data sets becoming larger, but the models themselves are becoming larger. The ability to reduce training wall clock time, and training wall clock time just means the total amount of time that has occurred. So real world time, not simulated time, not training iterations, not batches, not epochs. All of those things depend on the parallelism. So if you have 10 computers, you can go through batches in parallel, right? So you can 1,000 batches takes less time if you have 10 computers. But wall clock time is not dependent on any of those things. Wall clock is like your actual real time. Like someone sits there with a little stopwatch next to your computer, and as soon as you hit enter, they hit the clock, and then how long does it take until you're like, okay, I'm done. So that's wall clock time. Is a requirement for practical machine learning at scale. I don't know why they keep talking about practical here. Like it's almost like they're in denial that this is a theory paper. Optimizer scaling rules allows us to find faster learning procedures that produce similar results. So if you can scale this optimization process, you can produce similar results faster. And what do they mean by that? It means that anytime you're doing training, you're kind of just trying to get to the answer, right? So this is a pretty cool little plot here. So these are all neural nets, every single one of these lines, and each neural net has a different optimizer. And you can see how all of them end up at the same right answer, right? So if you were to let training continue for every single one of these neural nets, all of them would end up with values for the weights that are all very similar, that represent where the star is, right? The star is a specific values for the weights. This point here is a different value for the weights, and so on. But if you pick the optimizer right, and you pick the little hyperparameters within the optimizer right, you can just end up at the right answer way quicker in less steps, right? And that's what kind of optimizer and EMA, like that's what this whole idea is about. It's like maybe we can just get to the right answer a little bit faster by being a little bit smarter about the size of the steps that we take the direction that we take them in, and so on. Okay, so for example, the linear scaling rule for stochastic gradient descent, SGD, here you go, here's that old school 2014 reference right there, states that the learning rate should be scaled linearly with the batch size. So this is kind of an older, I in my head I think about that scene from Pirates of the Caribbean where they say they're not laws, they're more like guidelines, and I feel like the linear scaling rule to me is also kind of a guideline thing. It's basically just don't have massive learning rates with tiny batch sizes, because or else you're just going to be kind of taking big random steps all over your lost landscape that aren't meaningful. So there's a little bit of relationship there, but I wouldn't call it like a rule, and I don't know if it's linear is the best way to describe that scaling. Okay. This optimizer scaling works both ways. Access to larger computational resources means one can train equivalent models in reduced wall clock time. Alternatively, with access to limited computational resources, larger distributed computations can be replicated in increased wall time. Yeah, so running 10 computers in 10 times the amount of time is the same thing as running running one computer in 10 times the amount of time is the same thing as running 10 computers in one amount of time. So distributed systems, parallelism is kind of like just a fundamental property of computation. Many modern ML optimization methods incorporate a parameter exponential moving average. So an average over the parameters, where the parameters are moving over time, and the parameters that are closer to the current time, so the most recent updates, are exponentially more important than the updates of the past, or the values of the past, which is functionally a copy of the target model, except its parameters do not receive gradient updates and are instead a weighted moving average of the target model parameters. So here, in this particular formulation where you have a target model and then you have the online model, right, that's only one. There's only two models here. So kind of in the BYOL here, there's only two models. You have the target network, which is the value of this online network now, averaged with the value of this online network one step ago, averaged with the value of this online network one step ago, and then one step ago, one step before that. So there's only two, but you could have many of these online networks, is another way to extend it. But right here, there's just one online network and one target network, and the target network is the average, exponential average of the online network. Okay. These weights are updated by a momentum hyperparameter. So a hyperparameter is just a value that you have to pick as a human. There's no value that just falls out of the math. The math just says, hey, there's some beta and you have to pick some value for it, and humans decide on some values. They kind of make their best guess, and then over time, over the years, we end up with slightly better guesses about what a good value for this momentum hyperparameter is. And momentum just refers to the fact that, sorry I keep bouncing around, but there's kind of a notion of momentum in these optimizers. A lot of them, much like the ball rolling on a hill, if it's been moving in a specific direction for some time, even if it receives a batch that tells it to kind of move in a different direction, the momentum accumulated from previous gradient steps is going to kind of, much like momentum in the physical world with a physical object, it's going to kind of push it in the direction that it was moving in anyways. So, and this momentum and how much momentum matters and basically different properties of the momentum are usually hyperparameters. This functional copy, which we call the model EMA, so here they're talking about the target network, has a number of desirable properties. The model EMA inhabits a wider minima than the target model. Okay, never mind. Don't think of it as the target network because they're they're using target in a different way. So here they're talking about the target model as what they're, where is it? They're saying this network, here they're calling it the target network, but they call it the EMA network or the EMA model. And then the EMA model is targeting this model, which is called the online network, but here they're calling it the target model. So maybe a little bit confusing terminology, but maybe you can read around it. Reducing overfitting and improving generalization. Compared to the target model, the model EMA moves slowly, making it useful as a stabilizer for networks. So the model EMA moves slowly, and when you hear that move slowly, just think about this little SGD here, this little red optimizer here. You see how much slower it's moving? It's moving slower, but also look how much more certain it is, right? This green line, which has momentum, it moves faster, but it goes in a bunch of the wrong areas, right? It kind of like takes a bunch of steps, ends up in a bunch of nowhere, and then eventually gets to the right answer. But this more slower here, red, it kind of the direction is more certain, more correct. EMA model moves slowly, making it useful as a stabilizer for networks governing Bellman updates and reinforcement learning. So another deep cut here. The reinforcement learning is based on this Bellman equation, which is basically the discounted reward over some amount of time. Like, I don't know, it's not worth necessarily going into that because I feel like reinforcement learning is a bunch of garbage anyways at this point. But that's the old school reinforcement learning here. You have 2016 reference to this Lillicrap paper. The model EMA is relatively cheap to compute whilst providing a valid model but different to the target model. Okay, so obviously in today's GPU scarce, where GPUs are scarce and computation is a limited resource, you want to only do strategies that are cheap and easy to compute, right? If the exponential moving average was an absolute pain in terms of memory and time complexity to compute, then this whole area of inquiry would be worthless. But it's actually relatively cheap to compute, therefore it's worth looking into. This third property has made the model EMA a common choice for the teacher in many distillation setups. So this is more what I was referring to, where maybe you'll have multiple students. The students are taking gradient updates, and then the teacher is the average of the students. From semi-supervised learning to self-supervised learning, like Bootstrap Your Own Latent, Dino, and Data2Vec. So there you go. Despite its significant role in optimization, a recipe for adapting model EMAs when changing batch size has, to our best knowledge, been absent. All right, so nobody really knows. Like, this is not necessarily like eye-opening or anything like that. Like, most hyperparameters and most of the different choices in terms of the optimizers and the hyperparameters for the optimizers, and are we using weight decay and not weight decay, and like, nobody really understands the relationships between those things. That's why neural net or machine learning is often referred to as kind of like an alchemy, where you're kind of just mixing. You know, there's a alchemy was an ancient type of chemistry back in the days where people didn't really understand even what atoms were and what elements were, and they were just kind of like mixing random chemicals and things into beakers and trying to get stuff. And that's kind of where we're at with machine learning, where we know kind of what the pieces are and we understand some relationships, but we don't really have a theoretical basis from which to kind of come up with perfect answers. So we kind of have to try things out and experiment. So it's not that it's not absent in terms of like we have no idea, but we have a bunch of best practices, such as the one that they reference here, this linear scaling rule for batch size and learning rate. Okay. To address this, we derive an EMA scaling rule, which states how the EMA momentum P hyperparameter should be modified. So this is a rho, I'm pretty sure. Yeah, so it's a lowercase rho, and this this kind of comes from physics, but rho is usually used to denote momentum. So here they're kind of borrowing from physics and using the same term, except here they're going to be it's not momentum in the sense of like the momentum of a ball rolling down a hill. It's the momentum hyperparameter for this gradient descent, or specifically EMA process. Okay, so here we have definition 1.1. In these kind of like math theory papers, you're going to have definitions, you're going to have theorems, limitations. Here you have a theorem, a corollary. So this comes from the fact that in kind of like the more formal like math academic literature, like there's I think a little bit more prescription to the way that you write papers. Like we're used to reading machine learning papers on this channel, and in machine learning papers you have a specific structure and you can kind of make certain statements, but when you're writing math papers there's a higher level of requirement, and there's kind of like you have to specify everything in its specific theorems, and then it has to kind of like lead exactly to the next thing, and you can't like skip things and make general analogies or anything. Everything kind of has to prove the next thing. So you can see how, even though this is very much a machine learning paper, it's starting to bleed into that kind of math theory paper. Okay, so we have our EMA momentum P, and we're going to color that green. So if this is your first time on the channel, generally when we use this green highlighter color, we mean an equation term, and that makes it easy so that we can always scroll up and then see which terms in green. If we ever find something in an equation and we don't know what that term is, then we can look up here. Okay, so we have a definition of the EMA scaling rule. When computing the EMA update of a model undergoing stochastic optimization, so stochastic just refers to the randomness of this optimization. And why is it stochastic? It's because we don't actually know what the answer is, right? You don't know that this star is here. You're just taking gradient steps based on batches of data. But those batches of data are just a sample or an approximation of the actual underlying distribution. So you're kind of stochastically exploring the possible values for the weights. With batch size b hat equals kb. So, okay, so you have some batch size b hat, and then k is maybe a number to scale the batch size. Use a momentum p equals p to the k, p hat equals p, or rho hat equals rho k. Okay, so they haven't really told us what k is yet, and scale other optimizers according to their own scaling rules. I'm going to guess k is a scaling factor. So you have some batch size, which is a batch size maybe 232, something like that, and then k would be the number that makes it either big or small. So it's the scale on that batch size. The momentum rho, which is defined at batch size p, typically corresponds to a good hyperparameter choice. And here, kind of the fact that it's in quotations is kind of telling you that, yeah, we accept that this is a little bit more alchemy, although this does not need to be the case in general. In this paper, we make the following contributions. With the assumptions of Goyal et al., we derive an EMA scaling rule. The EMA update momentum should be scaled exponentially with the batch size. Okay, so I think this is... We're in the introduction section here. At the end of the introduction section, they're going to basically list the key contributions of this paper, and obviously the first one is going to be the most important here. And they're going to basically show you that this k value, which is used to scale the batch size, has some relationship to the momentum value, and they're going to argue that it's exponential, right? So previously, up until this paper, the way that we chose a value for this momentum hyperparameter, of which there's going to be several depending on your optimizer, and the batch size was some sort of good choice based on intuition and kind of like, hey, last time I mixed these couple chemicals together, I kind of got this result, so therefore I'm going to use something like that. Now they're going to give you a rule. They're going to say, hey, we're going to come up with a rule, and that rule is going to tell you if you have this batch size, this is what your momentum term is going to be. So, okay, to validate this EMA scaling rule theoretically, so this is going to be a validation in theory, we propose stochastic differential equations. Okay, so this is kind of differential equation. An equation is just anything in math where you have one thing equal to another thing, right? So everybody knows here's an equation. You have b hat is equal to k times b. So that's an equation. A differential equation is an equation where you also know the derivatives of that equation. You have kind of like a set of equations, right? And then stochastic means that some of the terms in that differential equation or little multiple equations are going to be governed by a random process, or some kind of randomness is coming in there. This is not a good definition of stochastic. Explain SDE, stochastic differential equations for me. Let's see. So we're going to give this to GPT-4, and I pretty much use Code Interpreter every time now. So we're going to give this to Bard as well, and then we're going to also give this to Claude. So I generally like to spread my queries amongst all the different AI systems. You know, I don't think I think we've shown that ensembles of language models are better than individual language models. So I will feed the same question to multiple language models, and then whatever the average of their answers is basically generally better than any individual answer. So there might be some mistakes in some of these answers, but the average of all their answers is very likely to be correct. Differential equations that involve one or more stochastic, aka random processes. There's some deterministic component as well as a stochastic component. Solutions are themselves stochastic processes, so you can't take out the noise. At some point, you're going to end up with the same noise term. Common applications include random movement. All right, let's see what we got here. Rate of change of y, so this is the derivative, right? So I guess that's a better way of saying. The differential is kind of a very ancient way of saying the rate of change. Now it means very different things, but differential equation is an equation involving an unknown function, so that's where the stochastic comes in, and its derivatives. Okay, let's see. Generalization of ordinary differential equations, which are equations that describe the evolution of a deterministic system. So ODEs, ordinary differential equations, are deterministic. SDEs have that stochastic part in it, which means that you can't predict it. There's some amount of noise, although I would argue that that noise isn't real, right? Reality is deterministic, so therefore that noise is simply just a process that you don't understand. It's some dynamic in the real world that we don't understand, and therefore we have to basically encapsulate it into this noise term in order for the math to work out. Okay. Completely determined by its current state. However, in an SDE, the future state is also affected by random events. Okay, so that's that. Let's move back. This model EMA contributes to the loss covering semi-supervised learning in SSL. We provided these approximations are first-order weak approximations. So first order means they only account for first-order effects, second-order effects, third order. Generally, that refers to the first order is just the equation. Second order is the derivative of the equation. Third order, the derivative of the equation, and so on. And that our EMA scaling rule is correct in the SDE limit under realistic gradient assumption. Okay, so maybe this is a little sketchy. Sometimes these theoretical papers, they put certain assumptions down, and by putting certain assumptions down, they constrain the theoretical guarantees to only those assumptions. And sometimes those assumptions are actually a little bit outlandish, or not outlandish, but not necessarily realistic, and therefore the entire theory paper is garbage. I don't think that's the case here, but it's always important to realize that as soon as you write some assumptions down and then prove some theoretical guarantee based on those assumptions, that theoretical guarantee, that rule, that insight is only as good as those assumptions are good. Okay, we empirically validate the EMA scaling rule first in a synthetic setting. Okay, so maybe they're going to be using some synthetic data here to generate a data set, followed by practical ones where the model EMA plays an increasingly significant role in optimization used during inference instead of the target. Okay, this is kind of cool. So maybe they have EMA for inference. Pseudo-labeling, where the EMA teacher follows the target and the student is optimized. Okay, so then they're going to have EMA in this kind of teacher-student paradigm, whose pseudo-labels are produced by the teacher, and then self-supervised learning, where maybe they have the there is no labeled data, but instead the data is maybe the representation produced by the teacher. So that is the label. We observe that pseudo-labeling and SSL dynamics during optimizer warm-up are not always able to replicate it at large batch sizes using only the EMA scaling rule. So some of these optimizers, you can basically have warm-up periods for them. So if we go back to our thing, this green momentum optimizer here, right? Let's say that instead of just taking gradient steps immediately, you instead held that little marble down. So that little green marble, it just wants to move immediately, but you hold it and you prevent it from moving it. And then you let a couple batches of data feed through it, right? So you're letting it warm up. And why are you letting it warm up? You're letting it warm up so that some of the parameters inside this green marble's movement or optimization process, they're kind of momentum parameters which are based on other parameters, right? So which are based on other gradient steps that it's taken. So that warm-up period is whenever you basically, you kind of let these optimizers warm up a little bit before they can actually change the values in the neural net. Those are usually common also for normalization. So maybe you want to normalize, but you don't want to normalize only based on this batch, and what you want to normalize based on a bunch of other previous batches as well. So that's another reason warm-up is popular. But maybe it sounds like warm-up causes issues with their EMA scaling rule. Enabling us to scale a batch size with BYOL vision transformers. Okay, so interesting. They're going to be doing the build your own latent, but in with a VIT, and it seems like the original BYOL was using ResNets, so kind of a more modern version of that. While maintaining performance of the batch size 4096 baseline. Okay. So interesting here, they're going to basically go from a batch size of 4096, right, which is pretty huge batch size. Like, that's not a batch size, especially for images. That's a very big batch size. That's a batch size that you would really only achieve in a big distributed training setup. But here they're saying that they can basically 10x that batch size and achieve the same result. Okay, to aid practitioners, we provide a scaling toolbox which gives practical advice. Okay, so we got a little scaling toolbox which gives practical advice. It's good to know. So if that's what you're interested in, if you more want to get a set of applicable tools and kind of heuristics that you can use for your kind of choices on your particular problem, you can just maybe go straight to this appendix C here and check out this toolbox. Scaling rules, weight decay scaling rules, so maybe how to pick the weight decay optimally, how to pick the right atom rules. So here's how you pick your betas. So here you go. You can pick your beta based on that, and then pick your beta 2 based on that. So this beta 1, beta 2 are the two values here, beta 1, beta 2. And actually here, you can actually also pick the epsilon. So basically everything is based off this K. It's basically once you pick a value for this K, you can just then go into these little rules here and then plug it in and find values for your betas, find values for your epsilons, find values for the weight decay that are based on that K. So you see here, it's based on this K here. Cool. The EMA scaling rule. All right. So now we're going to go directly into this actual paper here. We begin with an information discussion of scaling rules and motivate the existence of an exponential scaling rule for momentum values of the model exponential moving averages. Consider a model with parameters theta t at iteration t updated with SGD. Okay, so parameters theta t is basically just the values for all the parameters in a neural net. So for this fully connected neural net here, you're going to have weights at each of these neurons. You're going to have biases, and maybe there's like 20 of them, right? But for something like a big language model, you're going to have billions of parameters, right? So this theta t is literally billions of numbers. And then iteration t just means how many batches you've taken, right? And t describes the fact that training is a process that occurs over time, and maybe every single step here represents some time step t. Greetings, Hupo sir. Hello, Kalina. Updated with SGD, stochastic gradient descent. We stress the study momentum is not the focus. We refer to blah, blah, blah for discussion on scaling rules. Okay. So the stochastic gradient update for a model with parameters theta at iteration t given by a mini batch B. So here you have a mini batch, and the brackets here mean that this mini batch is a set, which is just a fancy way of saying a collection of things. Here the set is composed of x, b, So there's probably, here you go, B is defined as 1, 2, all the way to B. So there's a capital letter B, total samples, or total individual batches, or individual elements X within this batch. And here, this B equals the parallel bars like that, or pipes I think they're called, mean the magnitude. So the magnitude of this set B is just the total number of elements in that set, which is the total number of elements in this mini batch. And the elements in this mini batch, right, you could think of them as images. Maybe you have a batch size of 32, in which case the capital letter B is 32, and then you have each of the X's would be one image, and then they're sampled. That's what this little tilde means, from P of X, which is the true distribution of images. So all images in the real world that could possibly exist. You can think of it that way. And you have some learning rate. I think that's eta. Eta lowercase. Yeah, lowercase eta, which in this case represents the learning rate, which is something like 0.000001 or something like that. Okay, so now we have theta t plus 1 equals theta t. So theta t is the model parameter. So the values of the model weights at time t, and the models of the values of the model weights at time t plus 1. So this is basically one step of training, and the difference between the weights in one step of training is the learning rate times 1 over the B, the batch size. So the learning rate is scaled linearly with respect, or to the batch size here. You see how there's a 1 over there and then n, so n over B. So if you have a very big batch, this is going to become a very small number. If you have a small batch, this is not going to become a very small number. And here you have a summation over all elements in your batch. So all images, if you have 32 images in your batch, this is over all images. And this is L is usually the loss function. So maybe you have a reconstruction loss, which is the difference between the predicted image and the target image. Or maybe you have a classification loss between the predicted logits and the output logits, right? So this is your loss function. And your loss function, of course, is going to depend on the values of the neural net, because you're feeding something through that neural net and it's producing some output. And you basically are going to say, okay, well, here's what the loss function at those values are. I'm going to take the gradient with respect to that. So I have some target, something that my loss function is telling me I'm either good or bad at. And then I'm going to take the gradient with respect to that. We're going to take the gradient with respect to my model weights of that loss function. I'm basically going to get a little change. I'm going to get like a little delta that says this weight, in order for it to be more useful or better or more optimal for this loss function, you should push it a little bit that way, right? We should go a little bit that way. And that kind of basically is this process here, right? Is that really what the loss function is telling you is it's telling you, sorry, I'm like kind of scrolling through here. Maybe let me stay on that because I really do like this picture. Yeah. So the loss function is telling you, okay, the loss is a little bit lower over there than it is over here. So it's telling you the gradient. You're basically saying, okay, the hill seems to be going downhill in that direction. So let me take a little step in that downhill direction, right? This is the little step. This is telling you which way is downhill. And then the learning rate is basically how big of a step am I taking. And then that step here, that step is shown as a two-dimensional step, right? You basically, here your model weights are two-dimensional. You only have two parameters in this model. You have the parameter 1, you have parameter 2, and then you have the loss function. But it's weird to think about, but this exact same process is happening in a 70 billion parameter model. It's the same thing. You're taking a little step, except that little step, you're changing 70 billion values. So it's a little bit weird to think about. Your human brain has a hard time thinking about that, but that's basically what's happening. Okay. So the gradient with respect to the model parameters of this loss function is the parameter gradient for the sample x at iteration t, and the x sampled, or the x from this mini batch B, are independent and identically distributed. So what does this mean? It means that there's a little bit of an assumption here that you're pulling from this batch or from the real distribution. There's some real distribution of data, so some real distribution which would maybe be all images that could ever possibly be taken in the world. That's P of X, which you're never going to actually get. You're only going to get samples from that, and that you're assuming that those samples need to be independent and identically distributed in that. That's not always true, because generally you're always introducing some bias. So even just one of the most fundamental assumptions in deep learning, which is this IID assumption, is actually not true, because there's something, you're not actually getting IID samples from P of X. There is some relationship between these. It's just extremely difficult to formulate that relationship, and that relationship is going to depend on the type of data and P of X and all these different things. But if you don't have this IID, you can't do the math. So this is one of the kind of core assumptions. Okay, iterating over a sequence of independent mini batches. Okay, so that's basically training. When you're doing model training, you're just sampling a bunch of these mini batches, and then you're changing the values of the model parameters over time. Right? So at the very beginning of your training, here they're kind of choosing two random points in training. So you have some point in training T, and then some point in training T plus K. These are called steps, right? And adding up all those steps is going to get you to basically the same place that you would if you would have just taken those 10 steps. So here they're basically doing this here, but they're basically adding this total number of mini batches here. And it's like 2 for loops is basically what's going on. If the gradients vary slowly, okay, so if the gradient for one model is about the same as the gradient for a slightly different version or a slightly different copy of that model, then one SGD step equals n hat equals kn on a batch. So if the model isn't changing that much and the gradient with respect to the model is largely the same, then you can basically just add up the learning rates and take one step on a bigger batch, right? Where the batch here, so the learning rate n hat or eta hat is equal to the scaling k times eta. And then here you have the batch, this case the combined batch, b hat, is equal to the union of the 2 mini batches that they're talking about here, right? So basically, if you combine all these mini batches and the gradients are about the same, then you can just get there faster by scaling the learning rate. And this is not true. Like, I disagree with this, and the reason I disagree with this is because this is not correct. The gradients do not vary slowly. Sometimes you can take gradient steps and you kind of almost encounter I don't want to say discontinuity because it's a smooth landscape, right? But you can encounter these edges where suddenly the gradient becomes completely different, right? And landscape of neural nets. So I love showing this image here, this one here, right? Open in new tab. Where this is what we think of we envision the loss landscape to be this very, very smooth, very easy, kind of like you take it, all steps make sense because it's just this kind of smooth potato chip, right? But it's not like that. The real loss landscape for neural nets looks more like this. It's got all these weird hills and edges and kind of like steep drops and little shiny things like. So what I mean by that is that if you just take the model weights at some specific point, which maybe you're here, this is the same thing, 2-dimensional model here, and then the z-axis is the loss. So if you just take your model right here, and then you take one step and you're here, you're going to have a very different loss. And the gradient with respect to the weights, which is basically the pitch of this surface, is going to be completely different. So that's kind of my reason to be a little bit against this SGD scaling rule is because I think this assumption here in practice is not actually real. And that sometimes if you change the model parameters just a little bit, you end up with a completely different gradient, at which point adding up all the batches and then assuming that you can just add up the learning rates like that as well, I think that's incorrect. But as long as you're taking little steps, it's all fine. When running on SGD with a batch size B hat equals KB and a learning rate eta hat equals K eta. Okay, no, it's use. Okay, so for this batch size, use this learning rate. And that's the SGD scaling rule. For clarity in this work, we adopt the naming convention algorithm scaling rule, which means all parameters of those algorithms are appropriately scaled from batch size B to beta KB. Okay, so we saw how in Appendix C, they had a bunch of other scaling rules, right? They're going to talk about an EMA scaling rule. They're going to talk about a momentum scaling rule. And if you go to Appendix C, they have scaling rules for all these things. And RMS prop scaling rule, atom scaling rule, EMA scaling rule, weight decay scaling rule. And what they're telling you here is that anytime they say algorithm scaling rule, they're basically saying we're going to give you some rule by which you can pick all hyperparameters required in those specific algorithms. So in a atom optimizer, you're going to need this one, you're going to need this one, you're going to need this one, so you're going to need those three. And they're going to basically say atom scaling rule is going to be a rule that allows you to pick the values for all three of those with this K. So if you know for a batch size of 32, you're using this beta and 1 and this beta 2, then if you're now using a batch size of 64, which is twice that, then you basically do plug that K into the scaling rule, and it shall give you the updated values of beta that you should use. Okay. So although the assumption of slowly changing gradients is strong, okay, so that's exactly what I was saying, is that this assumption is actually not good. If it is true, then theta t plus k is not equal to theta hat t plus 1 only if n hat equals k, or eta hat equals k eta. Okay, the validity of the SGD scaling rule has been formally studied. In particular, there was ambiguity regarding whether the scaling should be a square root or linear. SDE approaches have resolved this, but have also been used to estimate the scaling K when the SGD scaling rule is no longer guaranteed to hold. Okay, and actually, one interesting thing that I feel like you guys might like about this is I know a bunch of you guys are involved in LoRa's, right? And you can think of a LoRa, or a low-rank approximation, which is a type of fine-tuning where you're basically training or learning these little delta W's, which are basically small changes. And you can think of each of those LoRa's as a small little step on this, right? A LoRa is basically like a little bit of training bottled up, right? So it's a little step, right? And what does that mean? Well, that means that if your neural net loss landscape looks like this, maybe when your diffusion model is here, it's very good at generating Pokemon, and when that diffusion model is here, it's very good at generating realistic food pictures or something, right? And what that LoRa is saved, what that LoRa is, it's basically that step. It's saying, hey, change these weights here, move them just a little bit in that direction, and you'll end up with a diffusion model that's good at generating Pokemon, right? That's what a LoRa is. Or you'll end up with an LLM that's expert in X, right? And then some people started suggesting, hey, well, maybe we can just add up all these LoRa's, right? Maybe we can take LoRa 1 and LoRa 2, and we add them up, and we get a LoRa that's kind of the combination of 1 and 2. And that kind of works, but at some point it starts to break down, right? If you start to add together multiple LoRa's, tens of LoRa's, hundreds of LoRa's, it doesn't work anymore. And why doesn't it work? And the reason it doesn't work is because this assumption here is because at some point that LoRa is saying take a little step down this hill, but then once you're down that hill, the other LoRa, which might be saying take a little step to the left, doesn't apply anymore because the landscape has changed. Now you're in a different part, and now if you wanted to actually move it in a direction to make things look more like Pokemon, maybe that would end up that would be a completely different delta W. So the assumption of slowly changing gradients is also the reason why you can't add up all these LoRa's. I don't know if that, hopefully that made sense for you guys, but I just think it's a beautiful kind of thing to think about. Okay. The EMA update for the model EMA, is this capital Eta? No, it's capital Zeta. Or no, it's just Zeta. Lowercase Zeta. Lowercase Zeta. Yeah. Okay, so this squiggle is lowercase Zeta. So the EMA update for the model EMA, which they're calling Zeta T here, and Theta T is the model parameters. Eta T is the model parameters exponential moving average. So target model theta. So anytime you see this Eta T, just think of it as basically the average of these Theta T's. At iteration T with momentum rho equals 1 minus beta rho. Okay, so eta at t plus 1 is eta t times some momentum term plus 1 minus the momentum term times theta t. So this is the exponential average, right? And it's the average of this eta and the current target model, but then the momentum term determines how important the previous guess was. Right, so how much momentum do we have in this current direction? If you have a lot of momentum, then you're basically just going to say, okay, let's mostly keep with what we already have, this eta t or zeta t, and let's only change it a little bit with respect to this theta t. If you have no momentum, right, then basically you're saying, I don't give a shit about what we had before. Let's try to do exactly what the theta t is. So the momentum term basically trades off between how much do you care about your current guess, your current zeta, versus how much do you care about what the target model has. And here they basically just redefine this momentum hyperparameter as 1 minus beta rho, just to make it a little bit cleaner, just so they have 1 minus beta rho here and then beta rho here, just because they don't like the rho 1 minus rho, so they're just defining this like, I think maybe conjugate, I'm not exactly sure what the math term is for this, but when you see that, where A is equal to 1 minus B, really, the reason they're doing that is just so that they can clean it up like this. Okay, the model parameters zeta do not typically receive gradient information. We take the convention that rho is close to 1 and beta rho subscript will be omitted where it is clear from the context. So this target model theta t is receiving gradient updates, right? So this theta t is changing over time with respect to the gradients that are coming from this loss function. But this eta t is not receiving gradients, right? It's changing over time just based on the values of these theta t's. Assuming again that the gradients change slowly, okay, so this is about the same as this. So here now they're basically just adding this eta in here. So given some eta, the gradient with respect to theta of this eta, again, the gradient, but now you see how it's t plus j here, t plus j, and then here it's t. So this is, the gradient step should be about the same whether you're at one specific value of theta or one specific value of zeta. But again, I would say that this is not actually a super strong assumption. There is a little bit of sketchiness to that, a little sus. And they're saying all of that is g. So they're just going to simplify it as g just because it's a huge pain to write this big giant term here. So they're just going to say that is g, the gradient. Gradient g. Here you go. Iterating over k independent mini batches produces model states this. Okay, so now they wrote it out kind of, and this is kind of like how you would write out a differential equation and then you would solve it with kind of matrix math, but here they're writing it out in this way because they're going to set it up for the differential equation. So, but really what this is just 3 equations just written as if it was one equation with matrices. So you have theta t plus k, so the model parameters at time step t plus k extra time steps, which represent the number of mini batches. is equal to 1 times theta t, right? So it's basically just equal to theta t plus 0 times eta t. So notice how there's no relationship between theta t plus k and zeta t, which is the EMA, and then negative learning rate times the gradient. Ooh. I just fucked this up. Okay, so that's theta t, and then here you go. 8 zeta t plus k is equal to 1 minus rho times theta t plus rho times zeta t, and then 0 times gradient. So notice how the 0 here means that this zeta t plus k is in no way dependent on the gradient. And then so on. And the gradient is only dependent on itself, and then they basically just rewrite it as this. So here's the 3 equations, which are largely the 3 equations that they put up here, right? 3, 2, and 1, except now they're basically just writing them like this. The first row is the SGD scaling rule. The second row is equivalent to a second EMA update, p hat, and we can take a single SGD update with batch size and learning rate, and a single EMA update, we get that. So that's the up to terms O n cross beta p, or eta cross beta rho. Sorry, I keep reading this as n, but it's not. This is eta, and this is rho, even though it's p. So it's a little bit confusing. This yields EMA scaling rule. The EMA scaling rule was derived for SGD, and it's extended to other optimizers in the following way. An optimizer scaling rule ensures that theta hat t plus 1 is theta t plus k. Satisfying identification for the first row. Next, the 0th order term n cross beta p, or eta cross beta p in the second row is optimizer independent. So they're saying this term here does not depend on the optimizer. And what do they mean by that is that the optimizer is largely how you're getting this G. So they're saying that here there's no dependence on G. So it's independent. It's going to work regardless of what optimizer you use. Finally, the first order terms are in the second row. This one here. Corresponding to the scaling rule error are an EMA accumulation of a target model theta under optimization, which is still O of eta cross beta rho, although its form may be different from other optimizers. Okay, so we made this approximation here, right? That I don't think it's necessarily a good approximation, but it's an approximation, and this whole thing depends on it, right? And we're going to take that approximation, and we're going to say, we don't know what's going on here. There's some underlying truth here. There's some secret property of the real simulation of reality, and we're just going to bottle it up into this term here, O of eta cross beta rho. And we're going to take that O of eta cross beta rho, and we're going to basically pull it out such that we have this set of equations here, but only one of them has this O of eta cross beta rho. And then we're going to say, we're going to call that scaling rule error. And this is a first order term. I wouldn't call that error. You know, I'm a little bit more in the camp that the universe is deterministic. There's no such thing as randomness. The randomness is just a behavior that we don't understand. So the way that I think of this is more, there is some way to describe this behavior perfectly. We just don't know what it is. So we're just going to put it here. We're going to call it randomness, and then we're going to call that randomness stochasticity, so that we can basically identify this as an SDE, right? If we knew what every single one of those terms were, then this would just be a system of ordinary differential equations, and then we basically just calculate it out and we're all good to go. But because we have that term, it's going to be a stochastic differential equation. It's going to be affected by random events, which is that term there, and so therefore we're going to have to use SDE solving techniques. The above discussion is intended to give an intuition as to why the EMA momentum should be scaled exponentially. As we have used the same slow-moving gradient assumption as the original SGD scaling rule, this may cast doubt on whether our rule is correct. To solve this ambiguity, we will follow Smith-Lee Lee al. Melody, and show that the EMA scaling rule is correct in the SDE limit under more realistic gradient assumptions. Okay, so I don't really know these papers here. Are these like, what are these? Smith and Lee 2018. A Bayesian perspective on generalization and stochastic gradient descent. Okay, so they're referencing other kind of hardcore ML theory papers here, but let's just keep going. The EMA scaling rule, let me take another sip of yerba mate here. Feel free to ask question, guys. This is like very dense, so it's difficult to parse. Okay. SDEs, stochastic differential equations, are a tool typically used to obtain scaling rules from first principles. In the following, we use SDEs to obtain a strong theoretical guarantee for the EMA scaling rule found in section 2.1. We consider the following discrete dynamics. So dynamics that are discretized, and they're discretized because we're taking discrete steps, right? Even though this makes it seem like it's a continuous, it's not continuous, right? Each frame of this GIF is basically one step. So there's kind of an inherent discretization to this optimization process where we're taking iterations, we're updating the values of these weights in discrete steps, right? And there's some underlying dynamics because of that. Okay, so we have our model weights at time k plus 1 is equal to the model weights at time k minus the learning rate times the gradient at time k. The gradient at time k is equal to the gradient of the function, which is the neural net. The neural net is parameterized by some model parameters theta k and the exponential moving average, the EMA neural net, which is zeta k, plus this term here, this sigma. I'm like super dyslexic. Sigma lowercase. I know I've looked this up on the thing before and it's a little bit embarrassing. Yes, sigma case, lowercase sigma times epsilon k, where epsilon k is this term which is dependent on the weights of the neural net and the exponential moving average of the neural net. This is like the quote-unquote noise, which I think is really just some pattern in the real world that is difficult to describe, so we just have to put it in a little box, in this little noise box, and just say that it's noise when really it's just we can't truly understand it. So this sigma is going to be the noise scale. So how important is this noise term, right? And then this capital epsilon theta k, zeta k is the gradient noise distribution. So whatever this quote-unquote noise is, it's going to be distributed, assumed to be a zero mean and variance sigma, capital sigma. So if that's capital sigma, what is that? Capital eta? So capital epsilon is the hard E. Capital sigma is the E with the triangles. But what is the E that is like curvy, right? What is this E? What should we call that? I think you can... What is the math symbol that looks like a curvy capital E? Do you guys know this one? How good is your math symbols? That's not the one I want. Element of. Bard thinks I'm talking about this term here, or this one. Element of this symbol, but that's not the symbol I'm talking about. I'm talking about this one. Can I copy this? Elise Lebeka, 5 pounds. Damn. Celebrate first super sticker. Let me give you a little party hat. I don't even know what to do. This is the first time I've ever gotten a super whatever. But thanks, Elise, or Ellie. Let's see what Bard says here. Random variable is distributed. The symbol E. Yeah, okay. It's not even coming up. So basically, I'm just going to call this big E. So big E sigma of theta k and zeta k, right? The model parameters and then the EMA model parameters is the noise distribution, and we're going to assume it's zero mean and variance. And if you look at your good old Gaussian, right, what does zero mean means? Zero mean just means that it's centered on zero. It means that the mean of this distribution on zero, and then the variance is basically the spread of that. So this orange one is high variance, this red one is medium variance, and then this blue one is small variance, and that variance term is capital sigma. So they're breaking it up into the variance and then the mean. For cat food, appreciate it. Independent of sigma, grad f, the gradient of this f is equal to the gradient of theta of this. Okay. We posit a dependency of the loss f, a public figure now. I'm going to buy an H100 GPU with that money. The loss f on the EMA zeta in order to cover semi-supervised and self-supervised. We posit a dependency on the loss on the exponential. That's kind of an interesting thing to think about. The case of Polyak-Ruppert averaging is covered by letting f be independent of eta. What? Okay. Is there an Eli 5 for Polyak-Ruppert averaging? I don't even know how to spell that. Eli 5. Polyak. Looks like lowercase epsilon. It does, but this is lowercase epsilon. Maybe I'm not. Maybe that's not lowercase epsilon. We need this. I need to have this like printed out. What do I keep calling epsilon then? Yeah, so if that is lowercase epsilon, then what the fuck is this? Because I called this epsilon. Jesus Christ. Too many. If only I wrote more papers, then I would know all the letters in LaTeX, and then it would just be super easy, right? Okay, but we were going to look at Polyak-Ruppert averaging. Polyak-Ruppert averaging. Let's see. Okay, all of these little LLMs are thinking about it. I got all my LLMs going out. Technique for reducing the variance of an estimate. Averaging the estimates from multiple iterations. It also helps smooth out the noise. Okay, so it's kind of like a little bit of a Kalman filter maybe. Averaging used to improve the performance and stability, especially in the training. If you're trying to find the shortest path, similar to training a machine learning model, trying to find the set. Okay, there's a little, maybe 2 Eli 5. Averaging helps to stabilize and someone is improved. So this is like a special type of EMA. Maybe it's just another name for EMA. Maybe it's specifically when you're doing EMA, little do you know you're actually doing Polyak-Ruppert averaging. And this is a kind of another annoying thing about math is that a lot of times the underlying mathematical concept is actually easier to understand than the name that is given to it. Like there's a lot. Sometimes you go into these math papers and you feel like you don't know what's going on, but really you do, and you have humans are pretty good at intuition, and you have an intuition about what's going on. It's just that over the time and over history, random people wanted to put their name on things, right? It's like people wanted to put ownership. So there's this kind of like historical legacy of usually white dudes putting their names on specific intuitions and kind of ideas, and there's like social pressure to remember the name of the dude that put his name on the thing. And I feel like I just find that really annoying. To me, it's just like, really the only important thing is the concept, not necessarily the fact that two dudes or one dude named Paul Yak Rupert decided that this type of averaging is going to be his type of average, right? I don't want to waste the limited representational capacity of my brain on storing this guy's name. You know, like, fuck that. So to me, I guess I'm just going to assume that Pauli Yak Rupert averaging is basically just a type of EMA. Okay. We aim to obtain an SD approximation of equation 5 as eta goes to 0. So this is the learning rate goes to 0. Generally, most learning rate scheduling is going to 0. So most of the time when you're training a neural net, your learning rate will start at a bigger number and then kind of go smaller and smaller and smaller and smaller, right? So, for example, let's do learning rate schedule. So learning rate schedules change the learning rate over time, and here's a very common, this is a pretty basic, usually they're more complicated than now. This is like, for example, a cosine learning rate schedule, but the kind of go-to vanilla learning rate schedule is something like this, where over the course of training, you're basically going to decrease your learning rate. So first time you go through your data set, let me scroll. Let me find that pick again. Right here. So your learning rate starts at 0.1, and then by the time you get to epoch 100, which means you've gone through your data set 100 times, your learning rate is now way smaller. So this is a stepwise learning rate schedule, so it's every X amount of epochs it switches, but you could have more complicated learning rate schedules. The scaling rule for iterations of theta is well known. We let sigma naught equals sigma square root of learning rate, where sigma here is the noise scale. The analysis of section 2.1 gives the scaling rule eta hat equals eta k and rho hat equals rho to the k. Linearizing this rule near eta equals 0 gives rho hat equals 1 minus k cross 1 minus rho, which is a linear relationship between 1 minus rho and eta. We therefore let beta 0 equals 1 minus rho over eta and consider the SDE this. Okay, so they have a limit. So the limit that they're considering is when the learning rate goes to 0. So as the learning rate goes to 0, can we start to make any assumptions based on these little equations that they wrote up here? So if we know that the learning rate is going to 0, and we have these little equations up here that have the learning rate in them, right, this little eta term here, does that tell us anything about where these equations are going? And here's what they come up with. They come up with delta theta t and dzt. So these are partial. This is usually when you have d something over dt, what that means is the derivative of that thing with respect to time. So here, this here is the derivative of z of t with respect to time. So they're just basically taking this dt, which would normally be under here, and then they're pulling it out into this side of the equation. And they're saying that dz dt, dzt dt, where z is at some specific time step t, is equal to beta 0 times theta t minus zt. So they haven't told us what this theta and this z is yet. I think it's down here. Let theta and z of t be solutions of equation 6. Okay, so there's some solution to this equation here, and the solution to that equation, we don't know what that solution is, but we do know something about the derivative of that solution, right? And that's kind of the whole, like, that sentence that I just said right there is literally the entire reason that this all works, right? Where this whole idea behind stochastic differential equations is that you might not be able to find the solution to it, especially if there's this stochastic process in one of them, but you can look at the derivatives of those equations, or the differentials, right, the derivatives with respect to time, and then say, hey, because of this derivative, we can actually probably infer some things about that solution. And that's what they're doing here. A Wiener process, in my mind, is just a stochastic, kind of like a Brownian motion. That's kind of what I think of in my head, but let me see. Is that correct? It's getting dense. Explain Wiener process. Is this PG-13? Am I allowed to type that into Google? Am I going to get banned? I feel like Claude might not like it. Let me see. Dog wanders around randomly. Yeah, so it's basically just like a random walk. Brownian motion. Okay, so it's literally Brownian motion. Okay. But again, that's kind of what I'm saying. Isn't it kind of annoying that in your head you know perfectly well what the concept of a random walk is, but then there's this guy called Brown who said, no, you have to call it a Brownian motion. And then there's this other guy called Wiener who said, no, don't. That's called a Wiener process. So in your head, rather than thinking, oh, random motions, think Wiener process. So I find this type of shit very annoying where you have to remember a bunch of old dead people's names. But okay, so basically, let's go back to it. The gradient of the function of theta t zt dt plus this noise scale times the variance here, variance of the gradient noise distribution. And here this 1/2 is basically just the square root of that. Okay, so this is kind of a little bit of a complicated process, but we can see that the different relationships here, there's only a couple things here. You have time. That's what the derivative is with respect to. You have theta and z, which are these solutions to the equation, and then you have this noise scaling term. So honestly, most of it is just defined with respect to those two things. SDE is an approximation of the discrete iterations when the learning rate eta goes to 0. An easy way to see this is that the Euler-Maruyama discretization of the SDE with a learning rate eta exactly recovers the discrete iterations. Okay, so discrete iterations, again, just repeating, why are these discrete? They're discrete because we're taking discrete steps. When you're training a neural net, you're taking steps. You're not just anything you do with a computer, right? The computer is doing specific steps. There's an inherent discretization to the steps that it's taking, and ultimately you're going batch by batch by batch, step by step by step. So there's a discretized optimization process here. And they're saying that, I'm not familiar with the Euler-Maruyama discretization of SDE, but it seems like what they're suggesting is that this discretization that they got to is basically the same thing as this Euler-Maruyama SDE. So I'm sure if you went and you looked this up, there'd be like some fucking medieval history paper where they showed how to solve an SDE in discrete iterations. More formally, we have theorem 2.1, which is the same spirit as those found in this. In the theorem, g of alpha is the set of functions with derivatives up to order alpha that have at most polynomial growth. Okay, so why are they introducing this set of functions with derivatives up to order alpha? The reason they're introducing that set of functions with derivatives is because we don't know what these solutions are going to be, right? All we have now is we managed to put our EMA and gradient update into a set of stochastic differential equations. Then we were able to basically say, here are some things that we can say about the solutions to those SDEs, and we're going to assume that RF is in that solution. Assume that F is continuously differentiable with F in this. So whatever our function is, which is our neural net, is going to be a solution to this SDE, and that solution is going to be in the set of functions with derivatives up to the order alpha, and the order alpha is 3. So a little bit of a mouthful for sure. Okay. Capital theta t and capital zt are solutions of equation 6, which is the motion being dominated or being that's dependent on this noise scale. And equation 5 with the variance equal to or in g squared. So in the set of equations, in the set of functions with derivative up to an order 2, which is 1 minus the set of 1 minus the order of the set of functions from which f is in, is the square root of the variance. So it's kind of a weird thing to think about, but think about it that way. The variance can't be basically, the variance is dependent with the derivative of the time derivative of this function f, which kind of makes sense. Okay, then for any time horizon t greater than 0, so as you kind of go further and further in your training, you're going to approach a horizon, right? The word time horizon there refers to the fact that you're taking steps over time. There's some horizon in that landscape, and it's like if you were to walk in that horizon in infinity, what would you get to, right? So in that time horizon t greater than 0, and some function g in the set of g to the squared, or g is the set of functions with derivatives up to order 2, there exists a constant c greater than 0. This is so gnarly. Independent of n. Okay, so there's some constant that is independent of the learning rate such that the maximum k from 0 all the way to t over the learning rate, where t is your time horizon, or the k that maximizes this term here, right? So the parallel bars go from here to here, which means the magnitude of this term, or the absolute value, of the expected value. So these fancy e's means the expected value. So the expected value of this, which is, you see how they've replaced, it's basically this exact same thing here, except they've replaced f with g, which is coming from this set g of functions, and here they're just plugging in, I guess this is the actual value of your model parameters and your EMA parameters, and then this is the kind of solutions to this Wiener process up here. I don't exactly know why the n is put in front of there. I guess they're trying to say k equals eta k. So the difference between those is going to be less than or equal to c by n, or c cross n. So that is hardcore. I'm going to be the first one to say that. That is very difficult to understand, but there is some theoretical guarantee here. Formalizes the intuition that the SDE is an accurate approximation of the discrete iterations. The SDE is an accurate approximation of the discrete iterations. So we're okay by looking at our gradient update, or what we're calling our SGD scaling rule and our EMA update rules. We're okay looking at this and thinking of it as a discrete stochastic differential equation. Okay. So now that we've proved that thinking about these as discrete SDEs is totally fine, let's go further. And okay, what are we going to do further? Corollary 2.1.1. Assume that f is continuously differentiable. So continuously differentiable just means that you can take the derivative at any point, right? So discontinuous, right? Everybody knows maybe this, but this is a discontinuous function, right? You can't take the derivative here because it breaks. You know, there's a break there. So continuous differentiable just means you can take the derivative at any point in time. It's smooth. With f in this set of equations g, and the variance, or the square root of the variance in this set of equations g. Okay, let theta k be and eta k be, where b is the training data set, right? It's the set of all mini batches. Be iterations of equation 5 with a batch size b and hyperparameters n and rho. So far, you basically have these two hyperparameters here. You have the learning rate, and then you have the momentum of your optimizer. And the momentum of the optimizer, that makes it sound like it's just one number, but usually it's a couple different numbers, and it's going to depend on which optimizer you're using. And here, I think actually that's not the, never mind, that's not the momentum term for the optimizer. That's the momentum term for the exponential moving average. So this is the EMA momentum, which I think they define up here. Yeah, so this rho here, which is a fancy looking P, is the momentum term for eta or zeta, which is the exponential moving averages of the thetas. Okay, let theta k and zeta k be iterates with batch size kb and n hat determined by the SGD scaling rule, and p hat determined by the EMA scaling rule. Then for any time horizon t and function g, there exists a constant c independent of n such that, okay, so basically they're setting up the same thing. So see this, like, these theorems have like a very specific set of kind of like every single word here has like a very form. There's no extra filler words here. The words are like ordered in a specific way. Like think of this like code. Like if I took this theorem and I got rid of one of these words in here, it wouldn't make any sense. It's like the words set up this exact. It's like because A, then B, therefore C, and such we can say D, right? And it's like I'm not like a math PhD, so I don't know. I'm not like, you know what I'm saying? I'm not like a 10x programmer when it comes to the math language, but that's just an important thing to realize here is that that's why they're being like so, the wording here is like so weird where they're like assume this with this and then let this be this, and then let this be this, and then thus by that we can therefore say that blank, right? So ultimately all they're trying to prove is this crap here, and they're trying to say that the K here that maximizes this, so this is basically the same equation up here, is going to be less than C cross N, where C is some constant times the learning rate. Okay, corollary 2.1.1. Yo, big fan here. Dor Yashar, thanks for the support, man. Appreciate it. This is one of those papers where you have to kind of really really dig deep in order to keep going, because it makes you kind of question whether you have the right brain for this. But the secret is that even the people that are very, very good at math, they still have a hard time. It's like everyone, your human brain is just not intended to be able to parse these things. You know what I'm saying? These are extremely difficult to digest. Every time I keep going back to this mental model of a little ball rolling on a hill, but realize that neural networks don't just have two parameters. Here it's like if we had a little neural net with two parameters, neural networks have billions of parameters. So when we're talking about taking gradient update steps in a billion parameter manifold, there is no human brain in the world that can actually visualize what the fuck that looks like. You know, even your most tenured math professor is probably has this mental model in their head, right? Everybody's just thinking about balls rolling on, or marbles rolling on a hill, because that's kind of what we're limited to. But realize that this equation is applying when this theta term here and this zeta term here are literally billions of parameters. It's just like some huge tensor of parameters. Okay. Close to the limit of small learning rate, demonstrating the validity of definition 1.1. So why does the limit of a small learning rate matter? Is because this entire part of the problem with what we're doing is that we're taking discretized steps. We're breaking down what should be a learning process, or this learning process, into a series of discrete steps, right? And if you have a big learning rate, you're taking big steps. If you have a small learning rate, you're taking small steps. So there seems to, at some point, you can probably come to the conclusion that, like, okay, well, what if the learning rate was infinitely small? If we were taking infinitely small steps, wouldn't we be following the perfect direction? And that's kind of why they kind of are leading with this of we want to know what the behavior is at a small learning rate, because if you could use a infinitely small learning rate and an infinitely large batch size, you would basically move only in the correct direction and get to the final solution in an optimal amount of steps. But you can't do that. You can't have an infinitely large batch size, and you can't have an infinitely small learning rate, which means that every single step you're going to take is going to have some stochasticity, some noise that is fundamentally coming from the fact that every time you sample a batch of data, you're introducing some bias there and some quote-unquote noise. Okay, a natural follow-up question is what happens when an adaptive optimizer, so some optimizer that adapts, is used instead of SGD? Maladi studied this without EMA and characterized how the hyperparameters change with the noise scale. In particular, they showed that under a high gradient noise hypothesis, so this is just a fancy way of saying that if you believe that your data set and your mini batch samples have a high gradient noise, right, then there is a limiting SDE. We derive the limiting SDEs for RMS, prop, and atom. These are just different optimizers. I think this is root mean squared prop, right? RMS prop. Let me just make sure. Root mean squared propagation. So it's a mini batch learning method. It's a type of optimizer. What the fuck? Why did this zoom out? Get a little bit bigger. Okay. Although a formal proof of closeness between the iterations that these SDEs is beyond the scope of this work, these SDEs indicate that the EMA scaling rule holds for adaptive algorithms. We demonstrate this empirically in section 3. Joseph Enochs. Damn, dude. 2 people. What am I going to do with all this fucking money? Like, damn, guys. Let me give you... I don't exactly know if you can see this, but I'm like emojiing your thing. Giving you some stuff there. Thanks for the super chat. This is weird. I feel weird. I feel like a... Like, did this just become like an OnlyFans? Is this like math OnlyFans? Okay. Now that we have experiments. Okay, so basically they went through this entire theoretical justification as to why you can use scaling rules that ultimately come from the solutions, kind of historical solutions to discretized stochastic differential equations for the dynamics between a model and the model's exponential moving average. So that's a summary of what we just basically proved through a bunch of math. I don't know if this actually counts as a formal proof. I think the requirements for a formal proving is a little bit higher, but the logic that was basically shown here. So now that we have all this logic, they're going to say, okay, well, we got these EMA scaling rules. Can we actually use this? Can we use these scaling rules? Are these actually useful? If we actually tried to mix chemicals in our little alchemy setup with these scaling rules, will we actually get anything better? And I think that's the most important thing to think about, where it's basically, this is ultimately a scientific hypothesis, right? We're coming up with a hypothesis, but unless you prove something with it, unless you show me that the real world actually behaves in the way that you just said it's going to behave, then I have no reason to believe you, right? So that's kind of the cool thing about this, is that if this was a math paper, if this was like some pure math PhD, the paper would end here, right? The paper would end here, and it would basically say, hey, I basically showed that because my logic makes sense, and I'm using logic from a bunch of other dead people who also used a bunch of other logic from a bunch of other dead people, therefore my stuff is correct. But that type of science is garbage, right? That's how you end up with string theory and shit like that, where basically we're like decades removed from anything that's actually provable, right? Like you're just using math and logic built on top of math and logic, which is built on top of math and logic. At some point, it's like, show me something in the real world that behaves in the way that you would expect based on this theory. So that's what they're going to do here. And what they're going to do is they're going to show that their scaling rules work if you actually try to train a neural net. And they're going to basically train a bunch of different neural nets here. Ordered by increasing influence. Okay. Role of model EMA in the optimization given a target model theta for different techniques, ordered by increasing influence of the EMA models. Assume a momentum of 0 less than or equal to rho less than or 1. So this is kind of the bounds that they're going to be trying for this rho. This rho parameter, they have to pick some value for that. So basically they're saying, okay, we're going to pick values for rho that are between 0 and 1. And the target model theta is subject to stochastic optimization at a batch size B. Okay, so we're going to pick some batch size B. We're going to pick some rho. We're going to kind of vary the rho. They're probably going to vary the batch size as well. And then we're going to have our target model theta. And then 3 different techniques here. What are this? Theta undergoes optimization and is tracked by eta, which does not affect theta. Eta is an estimate of theta with a time horizon and variance determined by B and rho. Okay, so they're going to do 3 different types of scenarios to test this out. In the first scenario, you're just going to have 2 networks. You're going to have your target model, which is the model that's actually receiving gradient updates. And then you're going to have this other model, the EMA model, which is going to be parameterized by these etas here. And that model is basically just going to be the rolling exponential average of theta. And they're going to say, okay, so this is like the simplest possible version. And they're going to say, okay, does it work if we just have the simplest possible version of this? Okay, now a more complicated, more practical, more realistic version of this is pseudo-labeling and then self-supervised learning. So pseudo-labeling is basically the same thing as this above one, except we have they're now calling the EMA model, they're calling it a teacher, and they're calling the target network a student. They're feeding unlabeled data, which is combined with labeled data. Okay, so they have some unlabeled data, which is probably going to be labeled by the teacher, and they're going to be training on batches that have some mix of labeled data, which is labeled by you, the human, and unlabeled data, which is labeled by the teacher. Okay, so a slightly more involved, more annoying version of it, but this is actually, maybe that's something that you could actually do if you were actually trying to solve something with machine learning, versus this is something that basically you would never do. And then self-supervised learning is something that people do all the time, and this is when there's no labeled data, and they're gonna, the optimization endpoint is dependent on beta and rho. Okay. So 3 slightly more, increasingly more realistic, but also increasingly more difficult versions of situations where you would use this exponential moving average idea. The H100 fund. Yeah, I realize my GPU setup is actually like trash at this point. You know, there was a point where, you know, I had my 3070s, my 3090, and I was like the cream of the crop in terms of like what people have in their home. But now I scroll through the internet and like people have like fucking like A100 server racks in their house, and I feel like a scrub, you know, because I'm still sitting on this 3090 and a couple 3070s. Like, what am I doing? You know, I don't have a server in my house. Maybe I need to get one of those tiny boxes, right? You guys heard about this tiny box from HOTS? Tiny Corp. I think he's trying to make basically these multi-GPU setups that you can buy in your house. Basically Ethereum mining rigs. You know, like there's a whole community of people that have been building these kind of rigs that you have in your house that you can supply with just power supply from your house and have like relatively normal cooling, and they've been using them to mine like cryptocurrencies like Ethereum, right? Ethereum mining rigs. So yeah, like something like this, right? So I bet you that the people that make these Ethereum mining rigs, I bet you they're all thinking about, how do I sell this to AI bros, right? Because all the crypto bros left crypto and came to AI. So if you were selling computers to the crypto bros, now you have to sell computers to the AI bros. So how are you going to sell them? And already here I see a ton of mistakes. You see here, so this is the power supply, and this power supply here, 1,000 watt power supply for what is this, 6 GPUs? That's not nearly enough. I have like a 1,000 watt power supply for a computer that just has 1 GPU in it. Like each of these GPUs pulls a lot more than that. Usually you have multiple power supplies. But yeah, here you go, 25K for this mining rig. This guy has 2 power supplies down there. All right, we're getting distracted, sorry. This is supposed to be a math stream. Thinking an M2 with 192 gigs. Yeah, I've used Apple computers before when I worked at tech companies. That's generally what they give you. Big tech companies, you get laptops and MacBooks, but I've always been kind of more of a Linux person. But yeah, like training stuff on MacBooks is like a whole other like dark art stuff. Like there's a whole Llama CPP. Yeah, this is like basically the bleeding edge of people trying to run or do inference on MacBooks. Mining rigs also have PCIe lane bottlenecks. Yeah, that's also a huge problem too, is that PCIe motherboard. Ooh. PCIe motherboard. I've shown this before, but in like a consumer motherboard, right, you have basically these slots. These are called PCIe slots, but every time open image in new tab. Let's go, let me see this one here, open image in new tab. So every time if you have 2 GPUs here, right, and you want to send one batch of something into another batch, let's say you actually have an exponential moving average. You have a teacher network, and that teacher network which is an EMA, right? An exponential moving average of your student networks, you want to update the models on your GPUs. So what you're going to have to do is the CPU is going to have to pull the models out of the memory, which is here, and it's going to have to send them into this PCIe slots. And then the PCIe slots are going to have to send it back to the CPU and then back to the memory, right? But so that seems very slow, right? It's like you have to constantly go back and forth between here, the memory, here, the CPU, and then here, the PCIe slots, which is where your GPUs are. But Tesla Dojo chips, that's not the way that people are doing it now. Like the people who are making these huge training rigs for like industrial purposes, they actually basically made everything vertical. So like the entire chip is basically all vertical so that it can communicate basically immediately with the things next to it, right? So this chip doesn't need to send information all the way to some CPU and then send it all the way back. It's basically communicating information with the chips immediately around it. Yeah, here, open image in new tab. So now the information going back and forth only needs to go a little bit, right? It just needs to travel a tiny little bit over here into this one, and then tiny little bit over here into this one, and tiny little bit into here into this one. So people are moving away from this kind of mentality of we have individual chips and then we have all these cables connecting these chips, and they're moving into this mentality of we have a computational mesh. You know, we have some mesh of computation. The computation just kind of like propagates and all the different things communicate in this mesh. So kind of a super cool way, but the unfortunate side effect is that the type of training that you can do at home is just going to become shittier and shittier and shittier. Actually, here's a better example of kind of what I was trying to show, right? Where in this dojo, which is a collection of these chips, right, the CPU communicates something to whatever this is. This is high bandwidth memory, HBM. That communicates to the tiles, and then the tiles communicate with each other. You don't have a situation where this tile has to send something to the CPU, which then sends it to the next tile, which is what would happen if you had PCIe like this with multi-GPUs. Okay, I'm getting distracted. You guys caused me to talk about GPUs here. Poly-Rupert averaging. When optimizing a model parameter theta, compute their EMA zeta and use zeta instead of theta at inference. Okay, so use the exponential moving average instead of the actual value of the model weights, because the exponential moving average is going to be a little bit more stable, and therefore it's probably going to give you a slightly better answer. But look at this, dude. This is like some 1992 paper, some 1988 paper. Like, I don't give a fuck about Rupert anymore. I don't give a fuck about this Poly-Yak dude. Like, why do we need to keep remembering this guy's name? Like, let's just forget about this guy's name. We're just going to call this using EMA weights at inference. We begin by showing the EMA scaling rule is required to match parameter trajectories in a simple setting. Consider the optimization of theta, right? So you're training your neural net to find the best possible value for your neural net parameters, which is theta, in a noisy parabola. So a parabola is just this, right? So some noisy parabola, maybe you can think of it like this in your head. You're trying to find the optimum value for W, and you keep bouncing around and taking updates. So you have your loss function, which is with respect to the model parameters. You have some A here. A greater than 0 is some curvature, which is some describing this parabola, and you have some scaled additive B. Okay, so they're kind of just making up some equation here. You have the weights at the next step is the weights at K step minus zeta, or the learning rate eta times the gradient at that step. You have the gradient at that step is equal to A times the weights at that step plus some epsilon K, where that epsilon K is a normal distribution with a mean of 0 and a variance of B gradient K squared plus C over K. So you have three different things here that are weird. You have this A, this B, and this C. And they're going to probably mess around with those A, B's, and C's and then see you how that changes. The scaling factor K in the covariance denominator. So the covariance denominator, this is the variance, or the covariance, and then here you have K, the denominator of that. implements the reduction in gradient noise at the scaling increases. Let theta in R, so the model weights are in the set of all real numbers, be optimized with SGD, stochastic gradient descent, and let there be a Polyak-Rupert average, eta, also in R. Okay, so you have your EMA also in R. With momentum, rho equals 1 minus beta for theta. At scaling k equals 1, we use the batch size, or beta b equals learning rate, eta b, equals 10 to the negative 4. So they're going to start with a learning rate of 10 to the negative 4, and they're going to run that for 10 to the 4th iterations. Actually, the correct color here, according to our color scheme, would be blue. Blue is generally the color scheme I use for numbers and numerical things. To yield a total time t equals IB cross NB equals 1. Okay, yeah, so if you multiply 10 to the negative 4 by 10 to the 4th, you get 1. To keep the gradients O of 1, so the order of the gradients is 1, and the gradient noise is non-negligible, we take A1, B 0.5, and C 0. Trajectory of the model EMA under different scalings. Choices for momentum with corresponding approximation errors. Figure 1. So that's this figure here. We show the effect of scaling by comparing model EMA trajectories of the baseline, k equals 1 black dashed. So the black dashed line is the baseline where you have k equal to 1. Then you have k equal to 8 and k equal to 256. And again, the batch size is just dependent on k. So if you remember, the batch size is like k times 1, I guess. Everything is dependent on k, right? The whole point of these scaling laws is that all of the hyperparameters are just based on the scaling factor k. So we can see that if you increase this k, your EMA positions, what is this, continuous time? The momentum according to different perfectly optimal, the approximation error of trajectories in the target model. Okay, so what are they showing here? Okay, I think I know what they're showing here. What they're trying to show you here is that they're trying to justify that their scaling law, right? And their scaling law for the parameter, or for the momentum, rho, was that the momentum should be equal to the momentum to the kth power, right? So this is the scaling law that they were trying to show. So what they're trying to show you is that if you plug in k equals 1, you get this black dashed line, which is this line here that goes down, right? It goes down to here. And they're trying to say, okay, well, if we say k equals 8 and we use the same rho as before, we get this red line. And this red line is different from this black dotted line. But if we take k equals 8 and we set it equal to, and we take our momentum and we set it equal to the momentum to the k, or k to the, or basically our momentum to the 8th, we end up with this blue line. And this blue line is right on top of this black line. So if we wanted to show that you should change your momentum rho here based on the k value according to our scaling law, rho equals rho bk, then we would want to show you that if you do that, the blue line is the same as the black line, and the red line is different from both of them. And that's what they're showing you here. So if you make k equals 8, the blue line is the black line, good to go. If you make k equals 256, the blue line is the black line, good to go. So far, so good. And then here they're going to do the same thing here. Here they want to show that the blue line is the same as the green line, I guess. What is this? Choices from momentum, approximation error. So this is the value for the momentum. And now it actually makes more sense. So this scaling law previously was kind of a weird, like why can you take this to the kth power and it's still meaningful? You can take it to the kth power because the value for this momentum rho term is usually something like 0.95 or 0.99, or here it's like 0.91 or something. And if you multiply 0.91 times 0.91 times 0.91 times 0.91, right, you're not going to get out of control. Because that value is always between 0 and 1, you can take it to the k equals 256 power, and you're still going to get something in between 0 and 1. So that's kind of why it works out. The approximation error of trajectories and the target model. Okay, so the model is this orange line here, and they're trying to show you that the EMA, or the ETAs here, which are supposed to be the approximation of the target model, right? The target model is the thetas, and the EMA is going to be the ETAs, which is going to be the exponential moving average of the thetas. Those should kind of end up in the same place, right? And that's what they're showing you here, is that if you're using the correct scaling law here, which is the law that they are trying to advocate for, then your exponential moving average model, your EMA model, ends up in the same place as your model that is just taking gradient updates. So that's what's going on with this figure. First, we observe the effect of scaling on a single run by tracking the position of a model EMA. We see that scaling at k equals 8 or k equals 256, the runs using EMA scaling rule match the baseline trajectory. And that's really all they're trying to show you here, is that basically it is what we would expect it to be. Whereas the model runs using the baseline momentum do not, even with a greater deviation reduced, included by greater scaling. There's a significant difference between scaled and unscaled, despite the seemingly small numerical difference of their momenta. Second, we consider whether EMA scaling rule is optimal. Okay, so we know that it kind of matches the behavior of the actual model, but is it necessarily optimal? To do this, inspired by the SDE analysis, we define the approximation error. Okay, so this is like basically the loss, right? You don't want this thing to be big, and the loss, it's going to be specific to the problem, right? So you're going to have different losses for different tasks, different data. But here they're kind of showing you the most simple version of this, which is kind of just the Polyak-Rupert averaging. And in the Polyak-Rupert averaging, all you want to do is just show that the behavior is the same and that this approximation error is roughly about the same here. Okay, test function G for given scaling K using momentum rho and the value momentum rho star that minimizes this error. Okay, so test function G basically means that we're trying to approximate some function G with our function F. And our function F is a neural net, but the function G can just be a random arbitrary function. Here, I think they're just calling it a noisy parabola. So for the purpose of just proving this theorem, the noisy parabola is going to be a parabola with noise, right? Where it has A terms, B terms, C terms, and it has some squared term and this theta term here. So rho star KG, so some scaling law is the rho which minimizes the error here, this approximation error. The approximation error is the K, which comes from either 0, goes from 0 all the way to T over eta, which is the learning rate, that maximizes the absolute difference between the expected value of the function G at the eta value parameters, or with the eta model, and then, or with the zeta model, which is the exponential moving average model, minus the expected value of this test function G for the exponential moving average model, zeta, at K over K. This is the same. I wish there was a better way to say K. Is it kappa? Is that the better way to say it? Kappa? Kappa and rho. Damn. Okay, so if you lay it out like that, you can figure out what the optimal K or optimal rho is. Let me see. ResNet 250. So now they're not just doing some weird arbitrary parabola. Now they're actually using a real neural net, and the real neural net is going to be ResNet 250, which is an old school style computer vision model, and ImageNet 1K is a computer vision data set. It's a classification task. You're classifying images into a variety of different categories, and here they're using different Ks. So at K equals 1, right, you're using a batch size of 1024 and a momentum of PB equals 0.999. So if we wanted to scale it down to a batch size of 512, right? Now let's use their scaling laws. Okay, so if we use their scaling laws, how do we adapt all the other parameters? Okay, well, if we scale the batch size down to 512, then that means we should basically, the K is 1/2. So that means that K is 1/2, which means that our momentum term should be PB to the 1/2. And if you do PB to the 1/2, you get 0.999. Where is it? Okay, so actually let's just look here. Bands indicate the mean and standard deviation across 3 runs. Okay, so you have different batch sizes. And when you have different batch sizes, that tells you what K is. So you have some baseline batch size, and then you have the batch size, which means you now know what K is. And if you know what K is, then you know what rho is, because rho from your scaling law can be calculated using K. And what they're showing here is that test top 1%. This is basically the metric that is used for ImageNet 1K. It basically means what percentage correct did you get on this classification task, and you have to get the first guess correct. That's what the top 1 means. Top 5 would be if you classify and your guess is within the top 5, and your top 5 guesses include the correct guess, then that's correct. Top 1 means it has to be correct. So here what they're showing you is that they converge to the same place. That's largely what they're showing you, is that this blue line and this black line end up in the same place. And here, train epochs, this is how many times you're training on the data set. So far so good. You know, they proved it for this simple situation here, and now they proved it for this computer vision version of the EMA training task. For scalings K equals 1 all the way to 1024, we determine the optimal momentum rho star and compare it to the EMA scaling rule. The scaling rule tracks until K equals 256, or kappa equals 256, and then rho star becomes systematically higher. We see target model increase at kappa equals 256 as the target model is EMA independent. This indicates that the SGD scaling rule is breaking. Interesting. Okay, so the scaling rules do break at some point. There is an inflection point in the EMA scaling rule approximation error before the model error grows. This difference indicates that the order of the learning rate times this beta rho parameter are beginning to influence the EMA update. So remember how at the very beginning of the stream and this paper, we talked about how the fundamental assumption here is that the gradient direction is independent of the parameter weights. But more and more we've realized that that's not the case, or we said that initially, but at some point that's going to break everything. And I think that's kind of what's happening here. These observations are true in 100 dimensions, and we stress that not changing the momentum at every scaling induces a large approximation error, indicating that there is merit to using the EMA scaling rule. Supervised learning on real data. Holy shit, dude, we're already at like 3 hours here? No, am I reading this wrong? 2 hours? Yeah, we're just a little bit over 2 hours. Okay, let's kind of speed up here. Okay, so now they're going to do the same thing, but they're going to do it on some semi-supervised learning on real data. So just a very supervised learning on real data. ResNet v2 on ImageNet 1K is supervised learning on real data, so I don't know why they had to pull that out, but that is basically the same thing. Image classification, okay, I guess this is exactly what they did. ResNet v2 on ImageNet 1K. It's a pretty standard example of supervised learning. Do not apply the EMA scaling rule on batch normalization. Batch normalization means you're normalizing every single batch based on the values in the batch. Statistics, we observe that without EMA scaling, there's a significant drop in EMA test performance, whereas with the EMA scaling rule, we can approximate the baseline model EMA test top 1 performance across all batch sizes. Blah, 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 due to a non-EMA performance dropping for high K. That model EMA top 1 is approximately 0.2, 0.3 higher than the target model. So remember, the whole reason we were using an EMA model is because the EMA model is going to be a little bit more stable than the normal model, which is just receiving those theta, delta theta updates that are based on gradient steps. So the fact that the EMA model is able to get slightly higher scores than the target model means that we're doing the right thing. At least we spent all this compute and time calculating the EMA. It better be worth it. And here we're learning, yeah, it is worth it because the final model that you get is a little bit more robust. And this makes sense, right? If you take your model and you're training it and you're feeding it batches and batches and batches and batches, that very last batch, it's going to maybe push it in a direction that isn't necessarily optimal, because that direction that very last batch pushes, that very last step that you take, is just going to be biased based on the last batch that you took, right? And there's some sampling bias when you sampled that particular batch. So you're better off making that very last step not count as much, and at that point, that's the whole EMA, right? So that kind of tracks in my head. Automatic speech recognition. We train a transformer, good old transformer architecture, good to know, using connectionist temporal classification loss. The fuck is that? And an atom optimizer on a train clean 100 hours of Libri speech. So Libri speech is some kind of speech recognition data set here, and it's about 100 hours of that. Okay. We apply the atom scaling rule and use dynamic batching. Okay, so the atom scaling rule is simply just the scaling rule, but applied to the atom optimizer, which is basically going to tell you which values you should pick for your betas and any other parameters that are in that optimizer. And I think that's plot is going to be somewhere here. Here you go. Transformer polyac averaging on Libri speech with different scalings K. So the baseline is this value for the momentum and this value for the batch size. 8 times 290s. The fuck does that mean? Dynamic batch size? We investigate dynamic batch sizes down to 2 by 290s up to 32 by 290s, and with and without the EMA scaling rule. Okay, so if your batch size is 8, your baseline batch size is 8, and then you're scaling, and then now you want to try a batch size of 2, well then that means your scaling is 1/4, so your K is going to be 1/4, and if your K is 1/4, then you want to pick a momentum that is your original momentum to the 1/4. So that's basically what they're showing you here is like the black line is the baseline, and then this red line is, okay, what if we decrease the batch size and then just chose the same momentum, versus what if we decrease the batch size and chose a momentum based on the scaling laws that we've argued in this paper. So they're showing you that if you decrease the batch size and you decrease the and you change the momentum based on the scaling law that they introduced in this paper, you end up with the black dotted line and the blue line are right on top of each other, which means that you correctly scaled the hyperparameter of the momentum such that it did not impact the training dynamics. Versus in the red line, you get a different behavior. In this case, it's kind of like a moot point because the red line also gets to the final answer, but the fact that it's not on top of the black line is the issue here. And here is just basically the same plot, but with other scaling laws. So let's say you had a batch size of 8 and you wanted the batch size to be 4. Well, now your scaling factor K is 1/2, which means that your momentum should be 0.9999995 to the 1/2 power. And the same thing here, squared, and here to the 4th power. And you can see how this blue line kind of sits right on top of this black line, which is what they're trying to show. And here you have the same thing, but for a different problem. Here you have transformer polyac averaging on Libri speech, and here you have transformer pseudo-labeling on Libri speech. And basically this is just the same exact plot that we've seen, where basically you change your batch size, which means you get a scaling factor K or kappa, and once you have that scaling factor kappa, that means you can adjust the hyperparameters of your optimizer and your EMA, which are this rho value. And if you do that according to the scaling law that they argue for in this paper, you end up with this blue line right on top of the black dotted line, which means that it's correct. You are scaling everything correctly. Okay. Blah, blah, blah. Student updates and model EMA. After pre-training, we continue training the student with both labeled and unlabeled data. The teacher first transcribing unlabeled data from the batch, producing pseudo-labels. So this is kind of the pseudo-labeling that they were describing, where basically the teacher, which is the exponential moving average, labels unlabeled data. So you're going to have some images that don't have a class. So maybe you have an image and you know that this image is a cat, and then you have another image and you don't know what that image is. So you feed that image into the EMA model. The EMA model will tell you this image is a cat, and then now you feed it as if it was labeled by a human or a ground truth label into the student. Okay. Observe that PL is essential to employ the EMA scaling rule to match the model trajectories. And that's really what they're showing you in all of these plots here, is that they're matching the model trajectories. You're getting the same trajectory if you use the scaling law as they have described it. The scaling rule does not match perfectly in the pre-training phase. This results in a significantly different PL quality. Okay, so they're saying here in the pre-training, the blue does not match the black dotted line. Can affect the training dynamics. To alleviate the Adams scaling rule mismatch, we postpone the pseudo-labeling until pre-training unlabeled data gives similar validation to WER. Okay, so here in the model warm-up, right, there's a warm-up period here where you're not changing the values of the weights. And they're saying that they were afraid of how the momentum terms in the atom were going to get affected. So they're going to postpone this pseudo-labeling kind of approach and only give the student batches of data that do not contain these pseudo-labels. So I don't know. This is kind of like a side note on a side note on like a technical point. Like, I don't think this matters. Okay. Scale by 1/k. ResNet 18. Bootstrap your own latent on CFAR 10. This is a very small, kind of older computer vision model. This is a very small, very old data set. So, take that with a grain of salt here. But the reason they're doing this is because you can train these things very quickly. So 100 epochs of CFAR 10. You can run that on your computer at home, no problem. 100 epochs of ImageNet 1K, that's a little bit harder to run on your home. 100 epochs of the training data set used for ChatGPT, you're never going to run that on your house. So the fact that they're using kind of smaller neural nets and smaller data sets is just kind of because they don't have the time, they don't have the resources. Okay, so here we have the same plots as before. We have you see how this is a little bit of a thicker line? Generally what that means is that they ran it multiple times. And because neural network training is a little bit stochastic, you're sampling from your batches. You're sampling batches of data from your actual data set. Those batches are going to be different if you have different starting seeds, which means you're going to result in different curves. So you're not going to get the same exact loss curve for the same hyperparameters if you change the random seed. And that's why there's a little bit of a thickness there, because sometimes it performs a little better, sometimes it performs a little worse. And that's where that thickness comes from. It's kind of the variance of the training run to the fact that you're sampling batches randomly. And ultimately, what they're showing here is basically the same thing, that the black dotted line is being tracked by the blue line. So the scaling laws largely approximate what you would expect. But there's a little bit of weirdness here. You see there's like weird behaviors here. There's this almost like a weird... Sometimes when you see this, like discontinuity like that, it's just because you got unlucky. It just means that you happen to sample a batch of data that was very unusual and kind of pointed the model in a different direction than it was used to, right? Like, let's say you're doing a cat and dog classifier. Most of the time, you're going to have 50% cats and 50% dogs in each batch of data, right? Each batch that you sample is going to have roughly 50% of cats and dogs. But sometimes you're just going to sample a batch and there's going to be 90% cats and 10% dogs. And the gradient step that you take from that sample is going to push you in kind of a weird direction, and your model's going to be a little weird. And that's kind of why you see these like little spikes. Obviously, that happens at a very small scale, and that's why it's a little bit noisy. And generally, when you're training classification models, you're making sure that that type of class imbalance doesn't happen, but the kind of intuitively equivalent version of that is happening whether or not you're actively trying to prevent it or not. At some point, because you're sampling from a data set, which itself is a sample of the true underlying data distribution, those samples are not going to be perfectly representative of the true distribution, and thus the gradient steps that result from those samples are not going to be in the perfect direction anyway, or either. Bands indicate mean and standard deviation across 3 runs. Okay. So here you have bootstrap your own latent with a vision transformer big. So there's different sizes of vision transformer. This is the big version, and it's 16 means it has 16 patches. Okay, similar thing here. They're basically going to start with a batch size of 4096 and this momentum, and then they're going to show how if you scale, try different batch sizes, that gives you what the value of K is, and the value of K gives you rho, which is the momentum, and so on. And self-supervised image representation learning. Finally, we turn our attention to distillation of self-supervised learning. So one last example, just to prove a point here. CFAR 10, ResNet 18 on CFAR 10. That's what we looked at. Vision transformer on ImageNet 1K. This is recovered from the learning process. The new model matches as this perturbation happens both in AtomW and SGD. So despite different optimizers, leading us to suspect this is due to the BYOL learning process rather than an artifact of the optimizer or momentum scaling. However, since this is not directly related, we defer this analysis. Okay, so they're saying there's a little bit of weirdness here. We don't know why these spikes are happening, but largely the orange line here, which is the scaling law that they want, is mostly tracking the original black dotted line, so they're happy with that. I'm kind of feeling this last sentence here, my brain is like starting to get a little bit fried here. So like I'm feeling the vibe that they're putting out there, which is like, dude, there's already so much shit going on. Let's just keep going. Let's defer this analysis for future investigation. We got to get this stuff done. Related work. Okay, so kind of a short related work section here, but here they're going to reference previous research groups that tried similar methods. Usually this related work is basically just kind of an insider trading Ponzi scheme to get your citations up. So generally these related work sections are basically the authors just referencing all their previous work so that they can get a bunch of citation counts. But, sometimes there's usefulness to it, I guess. SD has uncovered optimizer scaling rules allowed to understand of their limitations. SDs to uncover SGD scaling rule. SD's breakdown in terms of discretization. The SD analysis was extended to adaptive optimization, resulting in the atom scaling rule. So I guess the atom scaling rule originally came from this looking at these gradient update steps through the lens of stochastic differential equations, indicating that along with the learning rate, one should transform the beta 1 and 2 coefficients. These are the hyperparameters of the atom optimizer right here. You probably never even touch those, so now you can go into your code. If you're working for a startup or somewhere, you can go to the line where you create your optimizer and you can see that those aren't changed, and actually you can make these dependent on the batch size. So so yeah, if you want to be cool, you can go ahead and make a pull request into your model training code for your company where you make the beta parameters here dependent on the batch size based on this kappa, right? And reference this paper, and then when someone tries to fight you, you show them this math and they get scared. Okay, scaling rule. Varying the batch size during training. Smith investigated the benefits of scheduling the batch size at a fixed learning rate as an alternative to scheduling the learning rate at a fixed batch size. Okay, so the problem with this is that the reason the batch size is fixed is because your batch size is based on your GPU, right? You're just picking the biggest batch for your GPU, and then the learning rate is based on the batch. But here they're saying, hey, can you change the batch size and instead fix the learning rate? But that just sounds like a stupid idea because you're just like underutilizing the memory of your GPU. You might as well just max out the memory of your GPU. So this is a kind of a shit idea, IMO, as they are not intentionally replicating. This is in contrast with scales the hyperparameter to maintain the optimization process. Large batch training. SSL methods learn representations without labels. Self-supervised, right? You don't need supervision. You don't need labels. You don't need ground truth. You create your own labels. The network itself supervises itself. It is self-supervised. Large batch optimization is required to make use of this data in a reasonable amount of time. So if you're using self-supervised methods, you kind of want the very consistent, good learning rate steps that you get from a large batch. If you're doing some kind of self-supervised method and you have tiny batches, it's so noisy already because it's self-supervised that it's going to take a lot of time to get to the final answer. So the more noise there is in your gradient steps, and that's kind of hard to quantify, that doesn't have a specific definition. The noise can be related to the size of your data set, can be related to the difficulty of your problem, it can be related to the fact that your model architecture has specific strengths and weaknesses, but generally the bigger the batch is the better. Demonstrated algorithmic robustness when reducing the batch size through gradient accumulation and EMA update skipping, which implements an approximation of our EMA. Okay, so somebody came up with some weird like engineer solution here where they like accumulated gradients and updated EMAs, updated the moving average sometimes. And then here they're basically saying, okay, that's actually a version of the EMA scaling rule that we came up with. Our work provides a recipe to scale down and up in K, which they're showing. All these plots up here that they showed, you have K equals 1/2, but then you also have K equals 2. MoCo 3 enables contrastively distilled VITs. Contrastive learning is how CLIP was learned. So contrastive learning means that you're pulling things together in the latent space and then pushing them apart in the latent space. You're contrasting representations. Up to a batch size of 6144. Methods like Dino, this is the self-supervised vision representations that Meta trained, represent a worse scenario and are unable to scale beyond a batch size. In contrast, our work presents practical tools to scale large batch sizes in the presence of an EMA, enabling practical training of these SSL methods on large-scale data. And I think this also makes you think about the story, right? So we're reading a paper, we're going deep into kind of the technical details, we're going deep into the theory, we're kind of like connecting together the stochastic differential equation math of like the 1990s and 80s that they reference here to the modern deep learning kind of gradient optimization rules and EMA and all these kind of like collection of tricks that we've come up with and these optimizers. But why would people in Apple be doing this kind of theoretical work, right? Why would Apple, which is right now is trying to create a VR headset, and why the fuck would they be doing that? Why would they have people working on this shit in their company? And the reason is because I bet you they're trying to clone this Dino. You know, they can't use the vision representations in this Dino model because Meta released this paper, but the Dino paper, Dino V2 Meta, this Dino V2 model is, I'm pretty sure it's a non-commercial. Okay, I'm not about to read this license, but they can't use it. So Apple needs to train its own self-supervised vision representation. Basically, Apple wants to have its own version of Clip, its own version of Dino in-house, right? So in order to do that, it would be great if they basically could figure out how to make sure that their EMA and all their distributed training setups are actually getting to the final solution faster, right? So the fact that they have people working on the theory behind this EMA and kind of like distillation and these type of tricks that work well for SSL type learning, it suggests to me that they definitely have a team that's doing like big company distributed training. So that's kind of the intuition that I get, is that if they have theory people, they for sure have people actually putting these into practice. Show them this math and they get scared. Because they want to train on Apple Silicon. Yeah, I feel like they should make this, but with Apple Silicon, right? Like that, they should make a computation mesh that uses Apple M2 chips. Are they on M2 chips? Is there M3 chips? I don't actually know anything about fucking Apple hardware, to be honest. But yeah, I mean, this doesn't look good. So if this is the layout, right, the CPU still has to go through all this crap to get to this, the GPU and the neural engine. It'd be cooler if they kind of designed these in such a way that the neural engines can basically communicate to adjacent neural engines, kind of similar how you have here, right? Neural engine, that's kind of a weird terminology, but basically it's the GPU part, the thing that's actually doing the matrix multiplies. So I wonder if they're doing that. They probably have people that are, you know what I'm saying? The people at Apple designing the chips are definitely way smarter than I am. So they can see this trend coming, right, of the computation mesh. So I bet you that they're probably working on that. You're probably not too far off. Is that what an M2 Ultra is? Do they already do this? Am I just completely stupid here? What is an M2 Ultra? But this is still just one chip, and it's still just designed for one computer. They need to get to the point where they're basically making these big, huge setups, right? It's like they need to think in this term, like data centers, right? Like, I guess it's different because the reason Tesla want these data centers is because they want to train these giant AI systems. But like, is Apple really interested in training AI systems? Maybe. I guess they want to train Siri, right? They would want to train Siri in a big, giant, like server farm like this, at which point having the mesh makes sense. I don't know. Seamless training mat. Imagine laying down like you're laying down on a yoga mat, except you're laying down on this mat of GPUs that are all like burning. A large compute plane. This is so badass. All right, let's get to this conclusion. I gotta go do shit. We have extended the SD approximations to cover scenarios where a model EMA is present and can contribute to the model objective. From this approximation, we derive an EMA scaling rule. One should exponentiate the momentum of the EMA update to the power of k when changing the batch size. So this is their exponential moving average scaling law for the momentum term. So the exponential moving average requires this momentum term, and they came up with this EMA scaling rule, which tells you how to pick the right momentum if you know what k is, and k is going to come based on the batch size. As well as scaling other optimizer hyperparameters appropriately. Furthermore, the EMA scaling rule allows the extension of scaling rules to semi and self-supervised methods. We have conducted a wide range of experimental verifications, or empirical verifications. I would call them experimental, from supervised model tracking, speech and vision, pseudo-labeling in speech, image representation learning, blah, blah, blah. Using the EMA scaling rule enabled matching of training dynamics under batch size modification, whereas not using it resulted in significant differences in optimization trajectories. We were only able to scale BYOL SSL to a batch size of 245076, which is a fucking huge batch size anyways, like without any performance loss, only when by the EMA. While learning rate scaling rules are relatively commonplace in practical ML, the treatment of EMA is typically decoupled from optimization. We aim to bring the role of EMA to the forefront when considering the dynamics of optimization and what is going forward. the momentum will be treated and scaled correctly the same way that learning rates and other hyperparameters are scaled. Okay. What do we got in the abstract here, or in the appendices? Okay, this is going to get intense. Here you have the weight decay, the different scaling laws for other optimizers. Commonly used values of hyperparameters. You can probably come up with a scaling law for other hyperparameters. That's definitely future work. If you're interested in this line of work, I bet you could do that. I bet you could find some other hyperparameter and find a scaling law for it, and then reference this work, and then work at Apple. So how about them apples? Okay. Let's summarize this paper. Okay, so today we read How to Scale Your EMA. This is a paper coming out of Apple, and this is a relatively recent work coming in 2023. So this paper talks about exponential moving average, which is whenever you take your neural net, which is just a collection of weights and parameters, something like Llama 70B has 70 billion parameters, and you take the exponential moving average of those parameters during the course of training. So every time you feed a batch of training data into your neural net, you calculate the loss back propagates and tells you how much you need to change each of these parameters to take a little step and end up in a better place, right? There's different optimizers that allow you to take different steps, right? Bigger steps, steps with momentum, and so on. And those optimizers have certain hyperparameters, and those hyperparameters are sensitive to the batch size, they're sensitive to the learning rate, they're sensitive to all kinds of things. And people came up with these scaling laws for the optimizer parameters, and even a simpler version of that, which is the linear scaling rule, which is, hey, here's a rule that you can use, or a scaling law. Law seems like a little bit of a strong terminology. Law almost means like it's empirically true, or law means like kind of like fabric of the universe true. I would call these more like hypotheses. But the linear scaling rule says, okay, well, you can, if you know what the learning rate is, you can kind of determine what the batch size is. If you make the batch size smaller, you can change the learning rate and also make it smaller, or make it a little bit smaller so it doesn't fuck it up. So they kind of then said, okay, well, if you can do these kind of scaling laws for optimizers and for the batch size and learning rate, you could also probably do it for the exponential moving average. The exponential moving average, which a lot of people use because it moves more slowly and is a little bit more stable than the actual model weights, the exponential moving average has this momentum hyperparameter rho. I wonder if we could use those scaling laws for that momentum hyperparameter rho. And then they spend all this fucking time here. They go through all this math proof to show that the gradient updates, the discretized gradient steps that you take when you're performing training with a neural net, can be seen as stochastic differential equations. And if you can think of them as stochastic differential equations, that means that you can apply these solutions crafted by ancient people in the math department, and those solutions basically lead you to the point where you can say, okay, if you change the batch size, we can tell you what you need to do to the momentum of the EMA. So if you have a batch size that's 1024 and you have a momentum term of 0.99, and you want to say, okay, now I want the batch size to be 512, then we have now a scaling law, which is rho equals rho bk, which says that just take your momentum term and take it to the kth power of the scale, which is basically the batch size that you want now, divided by the batch size that you had before, and that'll give you a momentum that basically replicates what you had before. So now you have a scaling law that'll tell you how much you need to change the momentum of your EMA such that you end up with basically the equivalent optimization process as you would have with the original batch size. So now you have a scaling law for the momentum term of the EMA, and then they go on and they show theoretically why that works, but then they also go and they show for a variety of different models. So they have ResNets on ImageNet, they have transformer architectures on temporal classification, they have transformers on speech classification, and they show that for all of these, their theory is correct, and that if you scale the EMA according to their scaling law, you end up with a trajectory that is the same as the original batch size and momentum. So pretty cool little result, Still TBD as to whether this works in bigger models. I think it probably works, but everything that they showed you is only for these small models, and that's pretty much it. I think in Appendix C, they also give you scaling laws for other things. So this is a little bit more interesting. There you have, this is the original one that they reference. So this is, if you have a batch size which is scaled based on K, then this tells you the learning rate is scaled based on K. And they say, here's the RMS prop. So this is an optimizer called RMS prop, has these parameters beta. Here's how you can pick the beta parameter based on K, and here's how you can pick the epsilon parameter based on K. If you're using the atom optimizer, here's how you can pick the beta 1, beta 2, and epsilon, and so on. So little scaling laws that allow you to pick the right hyperparameters if you know what value your hyperparameters are working at a current scale. So definitely a mouthful. I might have lost most of you at this point, but hopefully you learned a little bit about EMA, about optimization, about intuition, about what are you really doing when you're feeding batches of data into a neural net and taking those gradients and changing the values of the weights of those ever so slightly. And like, how do the optimizers fit into that? How does the batch size fit into that? How does the learning rate fit into that? And maybe are there underlying fundamental laws to this discretized stochastic gradient steps that can be represented in equations, right? And I generally love these papers because you come out of them learning a little bit more and having a better intuition about deep learning and optimization and all these things. But then it also kind of shows you that there's some behavior underneath all of this. There's some truth. There is some law of the universe that is governing the dynamics of these optimization processes, this learning process that we go through. All right. So with that said, thanks Joseph, thanks Josh, thanks Ellie, thanks Dor, thanks Kalina, thanks Azur, thanks Alec, all of you guys, everyone, thank you for asking questions. Thanks for looking. Thanks for subscribing. If you're interested in any other machine learning papers that you want me to read, drop on the Discord and drop them in there. And I'm going to be doing streams tomorrow and Thursday as well. Still have to figure out what papers those are going to be, but tune in and figure it out. If not, have a great day and talk to you guys later. Peace.